first of all, this partial psi partial t on the left, I've got a 1 over I h bar when I simplify to just get partial psi partial t by itself. So this is 1 over I h bar Hamiltonian applied to psi as our replacement for this overall state here on the left. And then I've got q hat psi on the right. This middle term here is just going to be the expectation value of partial q partial t. Now, what on earth is that? Can I take the partial time derivative of an operator? Yes, if the operator has explicit time dependence. If the operator doesn't have explicit time dependence, then it's not going to have any partial time derivative. This term is going to be 0, and we're about to say this term is equal to 0 in a few minutes anyway. To give you an example of a situation where this term would be non-zero, think about something like the potential energy in the harmonic oscillator, where the spring constant of the harmonic oscillator is gradually being tuned. The frequency of the oscillator is changing with time. Perhaps the spring is getting gradually weaker, or the temperature is changing, affecting the spring constant. Under those circumstances, this term would be non-zero. The operator for, say, the potential energy in that quantum harmonic oscillator would be a time-dependent operator, and taking the partial time derivative would give you something that's non-zero. This third term, we can also apply a simplification. We've got psi on the left. We're not going to touch that. And on the right-hand side, we've got, let's see, 1 over I h bar. We've got a q hat and an h, and a 1 over I h bar there, acting on psi. Now, the next step in the derivation here, in considering how we can possibly simplify this, is we've got a term with qh bar, or q hat, h hat, excuse me, on the right, and a term here, h hat and q hat. So let's see if we can simplify this by applying the notion of a Hermitian operator to each of these terms. If I use the fact that h hat is a Hermitian operator, I can simplify, or not simplify, I can move the h. I can, instead of having h act on the left, I can have h act on the right. So this will become an h hat q hat acting on psi, similar to my q hat h hat over here. Now the other thing that I have to do in order to simplify these terms is to figure out what to do with these constants. Multiplication by a constant on the right does nothing. I h bar in the denominator, I'm just going to move that outside. So that will become a 1 over I h bar outside this expression. Now the 1 over I h bar here cannot simply be moved outside, and the reason for that is it's inside this left-hand side of the equation. So if I move it outside, I have to think about taking complex conjugate. So if I'm going to move this guy outside, I have to stick a minus sign on it because I've got an I in it. I have to flip the sign on it. Now if I do those two simplifications, first I have a minus 1 over I h bar. In this term, I have psi h hat q hat psi. This term, which I'm going to write next, is plus 1 over I h bar psi q hat h hat psi. And my remaining term over here is partial q hat partial t, expectation of that, whatever it may be. Now this overall expression here can be simplified even further. Here I have a h hat q hat and a q hat h hat. If you're seeing a commutator on the horizon, you're thinking the right thought. Let's combine these two terms together, these two expectations together, essentially factoring out the psi on the left and the psi on the right. What we're going to be left with is something like minus 1 over I h bar psi, and then the operator here is going to be h hat q hat minus q hat h hat. Factored out a second minus from the q hat h hat term here. And I've got psi on the right. And as before, I've got my expectation of partial q hat partial t coming along for the ride. So this term, now I can write that as I over h bar. If I multiply and divide both of these things by I, basically move the I to the numerator, flips the sign. I have here the expectation of the commutator of h and Q, plus the expectation of the partial derivative of the operator Q hat with respect to time. So this is a somewhat general result. Any time derivative of an expectation value is going to be given by a commutator of that operator that gives you the expectation and the Hamiltonian, plus some sort of explicit time dependence. If there isn't any explicit time dependence in this, what this tells you is that if the operator and the Hamiltonian commute with each other, if the commutator is 0, in other words, if HQ is equal to QH, then there is potentially going to be no time dependence for your expectation value. Essentially, time evolution of system as given by the time-dependent Schrodinger equation essentially ignores the expectation value of the operator that you're considering. It's some sort of a conserved quantity. That's a very useful sort of thing to be able to figure out. So if you've got commutator is 0, you're going to have a conserved quantity. Keep that in the back of your mind. Now, for the special case where the partial derivative of the Q operator itself is exactly 0, then what we're left with from the previous slide is that the time derivative of our expectation value of Q is equal to I over H bar times the expectation of our commutator H hat, Q hat. That was our general result. I just dropped the partial, the expectation value of this sort of term. Now, back to the notion of uncertainty. If I have the Hamiltonian and my operator Q as the two things that I'm considering, meaning I'm looking at an uncertainty in the Hamiltonian squared and the uncertainty in my operator Q squared. This is going to be our energy uncertainty. What is sigma Q going to be? Well, given this expectation of a commutator, that's the sort of thing that appears on the right-hand side of our generalized uncertainty principle. We had a 1 over 2i expectation of a commutator applied to this particular operator pair is going to be H hat, Q hat inside the commutator, all squared. So expectation of a commutator, I can rewrite that in terms of the time derivative of the expectation. So my right-hand side here, I can rewrite in terms of this as I've got my 1 over 2i as before. I got to solve for the commutator by multiplying through by h and dividing by I. So I've got an h bar over I on the left-hand side and d dt of the expectation value of Q. All of that's going to be squared. So simplifying this, I've got an I and an I, which is going to give you a minus 1 in the denominator, so I'm going to have a minus sign, but I'm squaring everything overall, so that's not going to change much. And what I've got for my right-hand side is h bar squared over, let's see. Let me write it as h bar over 2, quantity squared, and then I've got my d dt of the expectation value of Q squared. So what this tells you is that sigma h, sigma q, taking the square root of both sides of this equation, is going to be greater than or equal to h bar over 2 times this weird thing, the time derivative of the expectation value of Q. I'll put that in absolute magnitude sign to cover my bases in terms of square roots of squares. What this tells you is that the uncertainty in the value of an operator, the uncertainty in the operator itself, is going to be related to the time derivative of the expectation value of that operator. Essentially what that's telling you is that your uncertainty in the outcome of a measurement is going to depend on how quickly the quantity that you're trying to measure is changing. And that seems honestly rather logical. There is another factor here in terms of the uncertainty in the energy that helps bring things into focus further, though. So let's make a note of this result. It's nice and sort of qualitatively appealing, the notion that the uncertainty in an observable is related to how fast it changes, and the more quickly it's changing, the higher the time derivative of its expectation value, the larger the resulting uncertainty must be. But let's see if we can cast that in terms of that classic delta E, delta T uncertainty. If we're talking about delta E, that's essentially our sigma sub h. It's our uncertainty that results from a measurement of the energy, which is given by proxy in the notion of quantum mechanics, or the language of quantum mechanics, in terms of the Hamiltonian operator. And really we need some notion of delta t as well. What is delta t in this case? Well, let's define delta t to be something like the uncertainty in our observable Q divided by the magnitude of the time derivative of the expectation value of Q. This is sort of some characteristic size of change in Q multiplied by the rate of change in Q. So if this is some sort of delta Q over dq dt, this would give me some sort of a notion of delta t. More by dimensional analysis than anything else. Really what this means is sigma q can be thought of in terms of the time derivative of the expectation value of q and delta t, if I just say multiply this out onto the left-hand side, which says that this characteristic time that I'm interested in is the amount of time it takes the system to change by one sort of standard deviation of the observable in question. So this is going to depend on the observables that you're working with in some sense, but it is a notion of the characteristic timescale of change in the system. Now under these circumstances, our sigma h, sigma q expression is going to look like h bar over 2 when then we had the time derivative of the expectation value of q. That is going to be converted into delta E replacing sigma h, delta t replacing sigma q with this sort of expression. And then you can cancel out essentially this time derivative of q is going to appear both on the left-hand side and the right-hand side, thinking about it along those lines. And what we'll be left with is just that this is greater than equal to h bar over 2. So there you have it. We have derivation of the conventional energy-time uncertainty relation. What you should keep in mind here is that all of this was derived assuming a particular observable. So the potential results that you're going to get are going to depend on the quantity that you're interested in. If some quantity that you're interested in is changing very rapidly, then you're going to end up with a relevant delta t. This delta t is not just some time measurement uncertainty, it's a time scale of change of the quantity that you're interested in. So there has to be some sort of quantity in the back of your mind. You're not just saying delta t for the system, you're saying delta t for momentum, or delta t for position, or delta t for kinetic energy, or something like that. Regardless, the conclusions are the same. If the system is evolving rapidly, meaning with respect to the variable that I'm concerned about, the time derivative of the expectation value is large, then what that means is that delta t will be small, right? Large number in the denominator gives you a small number. And what that means is that the uncertainty in the energy will be large. Essentially what that means is if you have a system that is changing rapidly, it has to consist of a superposition of a wide range of different energies. You can only ever get a system to evolve rapidly with time if it contains a wide range in energies. And that gets back to the same sort of discussion we had earlier on in this lecture, where I said that the only way you ever got an expectation value to evolve was if you had a superposition of states with multiple energies. The wider the separation between those energies, the more rapidly the evolution would occur. That's reflected again in this energy-time sort of uncertainty relation. The flip side of this, if the system is relatively stable, what that means is that your system is evolving slowly with respect to the observable that you're interested in. So the time derivative of the expectation value of that observable is small. Then that means it will take a long time for the observable to change by one sort of standard deviation in the observable, which means our delta t is large. And consequently, our delta E can be small. We can have a small uncertainty in energy if we have a slowly varying system. If you have a system that's stable with time, nothing is changing very rapidly, then the energy uncertainty can be small. It can have a very precise energy. Keep in mind, these are all just inequalities, so you can have a very large energy uncertainty and a very rapidly evolving, and a very slowly evolving system. But at any rate, the last thing that I wanted to mention here is that all of this is really valid for any sort of Q. So this Q is representing any observable. What that means is that if anything is changing rapidly, then the energy uncertainty will be small. We can flip that statement around and say that the energy uncertainty will be large. We can flip that statement around and say if the energy uncertainty is very small, meaning we're dealing with sort of a determinate state, something with almost no energy uncertainty, then all time derivatives of expectations of any observable are going to be small. And we've said that before in the context of stationary states. Stationary states are the states that are eigenstates of the Hamiltonian operator. They evolve with time in a very simple way, and for a system that is in a single stationary state, the energy uncertainty is zero. Therefore, the delta t has to be a very, very large number, effectively infinity, in order for this inequality to hold, which means all changes in the system take place on a very, very, very long time scale. Everything is evolving very, very slowly. And in the sense of the true mathematical stationary state that is exactly stationary, nothing is allowed to change with time. Stationary states are truly stationary. So that wraps up our discussion of energy-time uncertainty. This is fundamentally different than the notion of position-momentum uncertainty, where both position and momentum are operators. But it does have some nice general interpretations in terms of the rate of change of expectation values of operators. So keep all of this in the back of your mind. It will help you interpret the behavior of quantum mechanical systems in general as they evolve with time. We started off this course by building a framework, talking about quantum mechanics in one dimension, where it is most simple and easiest to understand. Then we built up some formalism, talking about the mathematical structure of quantum mechanics. Now we're going to come back to where we started, except instead of talking about quantum mechanics in one dimension, we're going to talk about it in three dimensions. We live in three dimensions, so this is where the real-world examples start to enter quantum mechanics. First of all, how do we go from one dimension to three dimensions? If we're going to start off in one dimension, we ought to have counterparts for the concepts that we encountered in one dimension in three dimensions. In one dimension, we had a wave function, which was a function of position and time. In three dimensions, our wave function is going to be a function of position in three dimensions and time. Thankfully, it has not become a vector function. It is still only a scalar function, but it is now a function of 4 variables instead of only 1, or instead of only 2 here. We will see shortly that when we were talking about the time-independent Schrödinger equation, as derived from this full time-dependent wave function, we ended up with the solution to the time-independent Schrödinger equation were simply a function of position times e to the minus I energy time over h bar. We're going to find out something very similar happens in three-dimensional quantum mechanics. We'll get a function of position in 3 dimensions multiplied by the same exponential factor, e to the minus I energy time over h bar. The operators that will appear in the Schrödinger equation, for instance, in one dimension, we had, for instance, the position operator x hat and the momentum operator p hat. X hat and p hat in 3 dimensions are going to be vector operators. So instead of just having x hat, I'll have x hat, y hat, and z hat in a vector, or px hat, py hat, and pz hat in a vector. And the definitions here are more or less what you would expect. For instance, let's just say px hat is going to be minus I h bar derivative with respect to x. I have to start being more careful about the difference between total derivatives and partial derivatives now, since we're talking about functions with multiple variables. But hopefully the notation will become reasonably clear shortly. The full momentum vector operator here is going to be written then in terms of partial derivatives of x, y, and z. And we have some notation for that. Minus I h bar times this upside down triangle with a vector hat on top of it. This is the gradient operator from vector calculus, and this is going to be read as del or grad, or the gradient of, depending on whatever it's acting on. And this gradient operator here, as before, let me move this out of the way a little bit so my notation is less confusing. This full vector. One of the key experiments that really got quantum mechanics started was spectroscopy. Bright line spectra of the elements. They couldn't really be explained in the context of what physics was known at the time, and we've finally gotten to the point now where we can use the quantum mechanics we've learned so far to explain these bright line spectra. At least some of them, perhaps. This is the spectrum of hydrogen, this is the spectrum of mercury, this is the spectrum of neon, and this is xenon. So, 4 gases, and we'll be able to explain successfully the most simple gas possible, hydrogen. Our discussion of the time-independent Schrödinger equation in 3D, separated in spherical coordinates as appropriate for a spherically symmetric potential of a charged particle orbiting a nucleus, gave us psi with 3 quantum numbers n, l, and m. I'm not going to reproduce the long, complicated expression for what these are, but you know the radial part is given by the associated Laguerre polynomials, and the angular part is given by the spherical harmonics. As we went through the solution of the time-independent Schrödinger equation, we introduced a variety of constants, and then requirements, in particular for periodicity in the phi solution, the convergence and well-behavedness of the angular solutions, and convergence and well-behavedness of the radial solutions, gave us quantization conditions that we used to construct these n, l, and m. The constants that we got, for instance, we defined a k squared that was given by 2me over h bar squared. That should look familiar. We found out that that constant had to be given by 1 over some a squared, some radius squared, times an n squared quantum number. This a value, the Bohr radius, is about half an angstrom. And the energies that we got, after unwinding all of those definitions that we made, look something like this. You have the energy of the nth energy level, the nth stationary state with n as the quantum number, is given by this constant times 1 over n squared. And that constant should look familiar. It's minus 13.6, or it's 13.6 electron volts, with a minus sign out front, signifying that these are bound states. Their energy is less than the energy of a free particle. So minus 13.6 electron volts over n squared, those are the energy levels of our stationary states. Our stationary states are not going to be stationary in reality because atoms bump into each other and atoms interact in random ways that we haven't described the physics of yet. But suffice it to say, perhaps, that these energies are not going to remain forever fixed. If I prepare an atom in, say, the n equals 3, a quantum state with n equals 3, it's not going to stay there forever. After a while, it will lose that energy, and when it does, it will emit a photon. The changes in energy that take place are energy carried off by the photon. So we would say, for instance, that if we had, say, n equals 3 goes to n equals 2, there's a change in energy here, and we would say the atom has emitted a photon. Correspondingly, if you have an atom in state n equals 2 and it's excited up to state n equals 3 by an electromagnetic field surrounding the atom, we would say this atom has absorbed a photon. This absorption and emission of photons, photon here is our shorthand term for a particle of light, or quanta of light, perhaps I should say quantum of light, is really the crux of the matter here. All of our experiments that motivated quantum mechanics had somehow to do with the interaction of light and matter. With our treatment of the hydrogen atom, we now have descriptions of how we can calculate changes in energy on the matter side. We haven't really said anything about the photon side, and unfortunately for that we'll need relativistic quantum mechanics, which is a topic for another course. But at any rate, you know that light is going to be emitted and absorbed in quanta, and the energies of those quanta are going to be given by the changes in energy of the thing that we can calculate, the thing that happens on the atomic side. So these stationary states are not going to be all that stationary, and by plugging in numbers for initial and final energy levels, you can calculate out what the energy of the photon would be, what the change in energy of the atom would be. These transitions have names, and this is a very standard visualization of what those energies might look like. The y-axis here is an energy scale, and it has 0 at the top. Anything with energies higher than 0 is not a bound state. The thick horizontal lines here represent the energies of the nth energy level. Here is n equals 1, the lowest energy level, n equals 2, 3, 4, 5, 6, 7, etc., up to infinity, where the bound state isn't really bound anymore. It has essentially 0 energy. The transitions that are possible, for instance, if we're looking at the emission of light by a hydrogen atom, the atom is going to start in a higher energy level and drop down to a lower energy level. When it does so from an energy level 2, 3, 4, 5, 6, etc., up to infinity, all the way down to the ground state, n equals 1, we call that a Lyman line. The emission in the spectroscopic context has a particular pattern of energies that were first examined by, well, Lyman, and the lines are named after him. Transitions that start with 3, 4, 5, 6, etc., go up to infinity and drop down to the second energy level are called Balmer lines. Likewise, end-state lines with n equals 3 are Paschen lines. There are also bracket lines. You don't hear very much about them. Even less common are the Pfund lines and the Humphrey lines, which you can imagine have a final state of energy 5 and energy 6. So these transitions are the sorts of things that you would expect from the energy structure that we calculated as a result of the time-independent Schrödinger equation with a 1 over r potential. The transition wavelengths can be calculated pretty simply. What we have here is an energy that we can calculate, and we know the energy of the photon is going to be given by Planck's constant times the speed of light, let's say Planck's constant times the frequency, or alternatively, Planck's constant times the speed of light divided by the wavelength. Note that this is Planck's constant, not h bar, the version of the reduced Planck's constant that we've been using so far. So when you actually go out to calculate these things, you can calculate wavelengths easily by using the expression we had for the energy change by the atom. It's using that as the energy of the photon. The symbol for photon is gamma, typically, and solving for the wavelength. Doing so, you end up with this sort of thing, and this is a logarithmic scale now, 100 nanometer wavelength, 1000 nanometer wavelength, 10,000 nanometer wavelengths, and these things fall in very specific patterns. The Lyman series, which ended with n equals 1 as the final state, so this is a 2-to-1 transition, the longest wavelength Lyman line. This would be a 3-to-1, 4-to-1, 5-to-1, etc., all the way up to infinity to 1. Likewise for the Balmer lines, 3-to-2, 4-to-2, 5-to-2, 6-to-2, 7-to-2, etc., up to infinity to 2. Same for the Paschen series, and the bracket series, and the Pfund series, and the, I forgot his name already, the Humphrey series. They all have these nice patterns, and they all overlap. And if what you're looking at is the visible spectrum of hydrogen, you're looking at the Balmer lines. There are probably other lines that are visible if you look at a, quote, hydrogen gas, unquote, source being excited by a gas discharge, high voltage, for instance. Those are likely due to impurities. And if you think about the hydrogen atom, well, that's going to behave differently than the hydrogen molecule. It's going to behave differently than the singly ionized hydrogen molecule. And spectra like this, even with just a single atom, and this is just as predicted for the hydrogen atom with just a single electron, you already have very complicated behavior. So if I flip back to my motivating slide here, this is just looking at the visible portion of the hydrogen spectrum, and you can now identify this as the n equals 3-to-2 transition, this as the 4-to-2 transition, 5-to-2, 6-to-2, and if you continue into the UV, 7-to-2, 8-to-2, 9-to-2, 10-to-2, etc., these are the Balmer lines of hydrogen. When you work with more complicated atoms with more electrons, you have far more complicated behavior, and this is unfortunately something that quantum mechanics still really cannot predict well. To check your understanding of all of this, I have some simple calculations for you to do. First of all, figure out how the formulas that we gave for hydrogen would change for helium. You still have just singly ionized helium. So a single electron, instead of orbiting a single proton, orbiting an electron or orbiting an alpha particle, something with 2 protons. So the charge on the nucleus is going to double, and that will change the energies. Then make some calculations of energies, figure out whether they would be visible or not. And as finally, calculate the longest wavelength. Identify the transition for the longest wavelength in the line in series. These are conceptual sorts of questions that you need to understand the structure of the energy levels of hydrogen in order to answer, and there are also some simple calculations to do. But the fact that you are capable of making these calculations is really a triumph of quantum mechanics. We started with something that is essentially just an equation, hypothesized, almost entirely without justification. And it actually seems to work. You can do separation of variables, you can go through a lot of complicated mathematics, which from the physics perspective is more or less just turning the crank trying to solve this equation. And the structure that you get, subject to all of this interpretation we did as far as the probabilistic interpretation of quantum mechanics requiring normalization of the wave function, and the overall structure of all of this leads to calculations of real measurable physical quantities. And for instance, the answer that you'll calculate for this is something that you can look up. If you look up helium spectrum in Google, you will get lots and lots of matches, and some of them will include data tables with hundreds, if not thousands, of observed and identified helium lines. And the energies that you calculate, the energy that you calculate will be in that list. And that's really quite astonishing if you think about it. It speaks to the overall power of quantum mechanics. We started this chapter by considering quantum mechanics in 3 dimensions. The first tool we used to solve problems, to solve the time-independent Schrödinger equation in 3 dimensions, in particular, was separation of variables. We used separation of variables back in 1 dimension as well to separate the time evolution of an equation from the spatial evolution. That was how we got the time-independent Schrödinger equation from the time-dependent Schrödinger equation. In the case of 3-dimensional space, we also use separation of variables to separate the dimensions of space from each other. X from Y from Z, or in the case of spherical coordinates, which are most convenient for spherically symmetric potentials like we have for the case of the hydrogen atom, R from theta from phi. Another major difference between 3-dimensional space and 1-dimensional space is that in 3-dimensional space we have angular momentum. Angular momentum is not something that's going to fit into a single dimension, of course. So let's think about how angular momentum might behave in quantum mechanics. The approach we're going to take in this lecture uses operator algebra, the same sort of cleverness that we used back when we were talking about the quantum harmonic oscillator in 1 dimension with raising and lowering operators. We're going to take a very similar approach here. Back to basics though, first let's consider angular momentum. Angular momentum is what you have when you have an object and it's rotating about some axis. In classical physics, you're used to thinking about this as something like R times m times v, the momentum and the radius, mvr. The best way of expressing this in classical physics is as L, which is a vector, is r vector crossed with momentum vector, where r is the vector that goes from the axis to the object that's rotating, and p is the momentum, linear momentum, of the object that's rotating. We can make an analogous expression in quantum mechanics simply by replacing the arrows with hats. I know that's not terribly instructive, and we'll talk about that in more detail. But let's define a momentum operator, L hat, that's equal to r hat cross p hat, where p hat is a vector momentum operator and r hat is a vector position operator. Essentially, x hat, y hat, z hat as a vector crossed with px hat, py hat, pz hat, if I was writing things out in Cartesian coordinates. Now at this point, I'm going to save myself a lot of writing and drop the hats. I'll try and make it clear as I write these things down what's an operator and what's not an operator, but for the most part in this lecture, what I'm going to be working with are operators. This is an operator algebra lecture after all. So if you actually do the cross product between these x, y, and z operators, and these px, py, and pz operators, what you end up with is, well, you can do cross products, presumably. You end up with y hat, pz, sorry, I was dropping the hats, wasn't I? Y pz minus z py, that's our x component. Z px minus x pz, that's our y component. And x py minus y px, that's our z component. Now these are all operators, and they're the same sort of thing that you're familiar with. Y, and I'll put the hat on in this case, is going to be y, the coordinate multiplied by something. Whatever the operator is acting on, y hat acting on that is just going to be y, the coordinate times whatever it's acting on, the function in this case. Likewise, for instance, py hat is minus I h bar partial derivative with respect to y of whatever the operator is acting on. So these are the usual operators. We're just combining them in a new way, in 3 dimensions. Now, as far as answering the question of how angular momentum behaves, one of the interesting questions is it quantized, for instance? How should we describe it? The approach that we're going to take here is motivated by, for instance, when we were talking about the position operator, we considered the eigenstates of the position operator. Those were the Dirac delta functions. Those were useful. If you consider eigenfunctions of the momentum operator in 1 dimension, you get plane wave states, states with definite momentum. And of course, if we're considering eigenstates of the Hamiltonian, those are the stationary states. Whatever the operator, if we consider these states, the eigenstates of that operator, we get states with a definite value of the observable associated with that operator. This is especially interesting to do in the case of angular momentum. So, I said this was an operator algebra question. How can we analyze the algebraic structure of the angular momentum operators? Well, I said angular momentum operators there, and there are going to be 3 of them. I'm going to break it down into Lx, Ly, and Lz in Cartesian coordinates, because those are the coordinates that are most easy to work with. The way to think about these things in the operator algebra context is to think about commutators. And you'll see a very good example later on of why commutators are useful. But in this case, for instance, consider calculating the commutator of Lx and Ly. Now, I know what the definitions of Lx and Ly are in terms of their Cartesian coordinates, so I can expand that out. Y pz minus z py, z px minus x pz. That's what I get for Lx, Ly. And from that, I'm going to subtract z px minus x pz and y pz minus z py. So this is Lx, Ly minus Ly, Lx, just by the definition of the commutator. If I expand out each of these terms, for instance, you'll get, if I expand the term from the product of these 2 terms in the expansion, I've got a y, I've got a z, I've got a pz, and I've got a px. All of these coordinates are, in some sense, different, except for pz and z. Back when we were talking about quantum mechanics in 3 dimensions, at the very beginning of this chapter, we talked about the commutators of, for instance, pz and z being the same sort of commutator as you calculated in 1 dimension between, say, x and px. Y and pz, however, commute, as do y and px, z and py, etc. If the momentum and the position operators that you're considering are not the same coordinate, for instance, if I'm not talking about x and px, y and py, z and pz, the operators commute. So when I calculate the product here, y pz times z px, I have to keep the relative order of pz and z constant, but I can move the px and the y around wherever I want. What you end up getting for that, then, is something like this. I'll start at the left. This is going to be a kind of long and annoying expression. Apologies in advance. We're going to get a y, px, pz, z. So, y, and I have to keep the pz and the z in order, and I'll put the px on the right, for instance. Actually, you know what? I'll save a simplification step here. I'm going to move the px to the left because I can do that. Px commutes with pz and z, and just write pz, z. And I'll put parentheses around them to signify that I have to keep them together in that order. The next term I get, multiplying across here, I have a y, I have a pz, I have an x, and I have a pz. So I have a pz and a pz, and pz, of course, commutes with itself. It doesn't even matter the order that I write pz and itself. So for this term, I'm going to get something like minus y, x, and I'll write pz, pz, just writing it down twice. If I keep expanding out these terms, minus z hat, minus z, z, py, 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 px. It's hard to read my notes here, since my handwriting on my notes is even messier than my handwriting on the screen. X, py, z, pz, in parentheses again, from the contribution of this term. Comes in with the plus sign because we have two minuses. The z and the x commute as needed, as does the py and the pz, but I have to keep the z and the pz in order, so I've got z, pz, x and py being pulled out front. That's for the top two terms here. For the bottom two terms, everything is going to have a relative minus sign. So I'm going to get a minus and y px, z pz, plus z py px, plus x y pz pz, minus x py, and then pz z. So these are all my operators that I get as a result of expanding this out, provided I've copied everything down correctly from my notes. Now, if I've done things right here, you notice I have a z, py, px here, and a minus z, py, px here. So these two terms cancel out. I have a x, y, pz, pz here, and a y, x, pz, pz here. But x and y commute, so these two terms are actually the same as well, and they also cancel out. Another thing to notice here is here I have ypx on the left. These two terms both have ypx on the left. And on the right, I have things that don't commute, pzz and zpz. So this term here, I'll write it in black, I can combine these together. I'm going to have a y px, and then a pzz minus zpz. And you know what that is. That's the commutator of pz and z, the operators. I can make the same sort of simplification over here. I have an xpy on the left, and I have a commutator of pz and z over here on the right, plus xpy, z, pz commutator, coming from these two terms. Now you know what the commutator of pz and z is. The commutator of z and pz is I h bar. This is the reason we like commutators. Commutator-like expressions often appear in expressions like this and allow us to simplify things, in this case just down to a constant. So this guy is going to be I h bar, and this, which is the same commutator only with the order reversed, is going to be minus I h bar. You can easily verify for yourself that swapping the order of the arguments in a commutator gives you minus the original commutator. So what I'm going to get now, at the end of all this, is y, where'd it go? I have a minus IH bar and I have an IH bar here, so I'm going to factor that out, and I'm going to have a YPX and an XPY, which should start looking familiar. YPX and XPY appears in LZ. So this overall expression is just going to be IH bar LZ. So we started out calculating the commutator of LX and LY, and we got IH bar LZ. You can write down expressions for all of the commutators in this way. The commutator of LX and LY is IH bar LZ. The commutator of LY and LZ is IH bar LX. And the commutator of LZ and LX is IH bar LY. Likewise, if you swap the orders, you get minus signs. These are the commutators that are going to be useful to us in considering the algebra of angular momentum. If you feel the need to memorize formulas like this, note that the order these expressions always come in is always sort of cyclic, always sort of alphabetical. X to Y to Z and back to X. Here I have X, Y, Z. Here I have Y, Z, X. Here I have Z, X, Y. Always going around in this sort of clockwise order. You see a lot of sort of cyclic or anti-cyclic sort of permutation type arguments associated with commutators like this, and this is the first time that this sort of thing has shown up. So one thing you notice right away is that LX, L, and LY don't commute. We didn't get 0 for the right-hand side here. What that means is that if you want to determine simultaneously LX and LY, you have to consider the uncertainty relation between LX and LY. If I want to simultaneously determine LX and LY, the generalized uncertainty principle from the last chapter tells me that the product of the uncertainties in LX and LY is going to be given by the commutator of Lx and Ly. And if you go back to the previous page and figure out what that expression actually looks like, you get h bar squared over 4 times the expected value of Lz squared. So if I have some angular momentum in the z direction, I cannot simultaneously determine Lx and Ly. What that means is that if I'm considering angular momentum, I shouldn't be thinking about the angular momentum in the x direction or the angular momentum in the y direction. They're not very convenient observables to work with. What is actually a convenient observable to work with is L squared, which is defined to be the sum Lx squared plus Ly squared plus Lz squared. Essentially, the squared magnitude of the angular momentum, if you wanted to think about this in the classical context. This is sort of like saying r squared is the total length of a vector. So the question then is, how does this L squared work? One thing you can do with this, L squared, since we're calculating commutators, is ask what's the commutator of L squared with, for example, Lz. Can I simultaneously determine one of my angular momentum direction coefficients with this total angular momentum squared sort of operator? What is this commutator equal to? Well, this L is going to be Lx squared plus Ly squared plus Lz squared, and we can separate out those commutators. Lx squared commutator with Lz plus commutator Ly squared commutator with Lz. And the third term is commutator of Lz squared with Lz. Now the commutator of Lz squared with Lz is just going to be 0. This term drops out. This is going to be Lz, Lz, Lz minus Lz, Lz, Lz. These two commutators we have to treat in a little more detail. So let's expand them out. This is going to be Lx, Lx, Lz minus Lz, Lx, Lx. And this is going to be Ly, Ly, Lz minus Lz, Ly, Ly. You can simplify this expression by adding and subtracting the sort of missing terms, if you think about this. Here I have two x's on the end in Lz. What about Lz in the middle? So let's add and subtract Lz in the middle here. I'll write this as minus Lx, Lz, Lx plus Lx, Lz, Lx. So I haven't actually changed this expression any, I've just added and subtracted the same quantity. In the operator case, the addition and subtraction gets a little bit more difficult to understand, but this is essentially an identity. And I can do the same sort of thing here. I'll write minus Ly, Lz, Ly plus Ly, Lz, Ly. Now this we can actually work with. If you notice, here I have an Lx on the left, and then an Lx, Lz minus Lz, Lx. So if I was treating these two terms just by themselves, I could factor out an Lz on the left, and I would be left with a commutator of Lx and Lz. That would end up looking like this. So this is still an equality. Lx on the left, and then Lx commutator with Lz. Accounts for this term. This term is accounted for in much the same way, except I have to factor an Lx out to the right. So this is going to give me an Lx, Lz commutator with an Lx on the right. I can make the same sort of simplifications over here for exactly the same reasons, and I end up with pulling the Ly out to the left, Ly commutator with Lz, and pulling the Ly off to the right, Ly commutator with Lz, Ly on the right. So, still equal to my original expression. I haven't really made very much progress, but I know what the commutators of Lx and Lz are, or Ly and Lz. Those were the commutators I calculated on the last page. So this does actually simplify things out. The commutator of Lx and Lz is minus IH bar Ly. So this whole thing is going to be Lx. I'll stop writing it in square brackets because it's not a commutator anymore. Minus IH bar Ly. What I get for this this commutator is the same. It's going to be minus I h bar Ly Lx plus, over here, I've got Ly on the left, and these commutators are in alphabetical order, so I'm just getting positive I h bar plus I h bar Ly. Now, oops, I forgot where to go. I forgot my operator. The commutator of Ly and Lz is not just I h bar, it's I h bar Lx plus I h bar Lx Ly. Now, if you notice here, here I have an Lx followed by an Ly. I have to keep these in the right order because they don't commute, but I have a minus I h bar Lx Ly. I can bring the minus I h bar out front. Here, I have an I h bar Lx Ly. So, minus I h bar Lx Ly plus I h bar Lx Ly. These two terms cancel out. These two terms, here I have an Ly Lx, here I have an Ly Lx. Here I have a minus I h bar, here I have a plus I h bar. These two terms cancel out as well. So essentially what we're left with here, since everything is canceled, is 0, which means that L squared does commute with Lz. L squared, commutator with Lz, is equal to 0. This is the result that we hoped for. It means that we don't have a generalized uncertainty relation between Lz and L squared, which means I can simultaneously determine both L squared and Lz. That means I can hope to find eigenstates states that are both eigenstates of L squared and Lz. And that's really what we want. When we're done with this, we want something that's easy to work with, and eigenstates are especially easy to work with. So, we've worked out the general algebraic properties of angular momentum operators. And we've settled on working with this combination L squared and Lz. Those are operators that we can hope to work with. And what we're hoping to find are eigenstates, things that we can, most easily work with. So, how are we going to proceed? The way we're going to proceed is ladder operators. This is the same approach that we took back when we were doing the one-dimensional quantum harmonic oscillator. It was difficult to explain then, and it's difficult to explain now. Fundamentally, if we're working with L squared and Lz as our operators of interest, consider this just a definition. L plus or minus is equal to L sub x plus or minus I L sub y. These should look a little bit familiar, and we're in the end going to make the same sort of cleverness arguments that we made back when we were doing the quantum harmonic oscillator. But for now, let's just consider the properties of these L plus or minuses. We're doing algebra with operators, and we were calculating commutators. So let me ask you the question, what is Lz commutator with L plus or minus? Well, you can substitute in the definitions of Lz, L plus, and L minus. And since the commutator is linear, I can just split this up into two separate commutators. Lz commutator with Lx plus or minus I times Lz commutator with Ly. You know what both of these commutators are. We've already calculated them out. You get I h bar Ly plus or minus I times z and y here now are in the wrong order, so I'm actually going to get a minus I h bar Lx in this case. So this is our commutator, and if you simplify that down, you'll find that this is actually equal to plus or minus h bar L plus or minus. So calculating the commutator of Lz with L plus or minus gave me something relatively simple. It just gave me L plus or minus back. If I ask you the question, what is the commutator of L squared with L plus or minus? Again, you can expand out the definition of L plus or minus, L squared Lx plus or minus I times the commutator of L squared and Ly. But you know L squared commutes with Lx and L squared commutes with Ly. These are essentially the same as it commuted with Lz. So without even calculating anything here, we know the answer is 0. So this is the algebraic structure of these ladder operators. The key fact that I mentioned earlier is that what we're looking for are eigenstates of both of these operators simultaneously, simultaneous eigenstates like that. Essentially, the question that we need to ask that we can use these ladder operators to answer is if we have some state, and I'm just calling it f here, if L squared f is going to be given is an eigenvalue, if f is an eigenstate of L squared, it would have an eigenvalue lambda, for instance, and f is a simultaneous eigenstate of Lz, it would have an eigenvalue, for instance, mu. What about L plus or minus acting on f? Now the terminology here should be suggestive. I call these things ladder operators. Let's see what that actually gets us. First of all, consider L squared acting on this, L plus or minus f, acting on f. Well, you know that L plus or minus commutes with L squared. So I can write this as L plus or minus times L squared acting on f without changing anything. But L squared acting on f, I know what that is. It's just an eigenvalue multiplied by f. So this is L plus or minus times acting on lambda f. Lambda just being a constant can be pulled out front. So I've got lambda and then L plus or minus f. What this tells you is that L plus or minus f, if f is an eigenvalue, f is an eigenstate of L squared, L plus or minus f is also an eigenstate of L squared with the same eigenvalue. I can ask the same question of Lz. What does Lz do to this mysterious quantity L plus or minus acting on f? This is a little bit more complicated, and I can simplify it by rewriting it slightly. Let's say this is Lz, L plus or minus. Now I'll write this as minus L plus or minus Lz plus L plus or minus Lz. I've just added and subtracted the quantity, and you can see what I'm trying to do now. I'm trying to arrange things such that I get commutators, as well as things that I know, because this is all acting on f, and I know what Lz does to f. It just gives me an eigenvalue. So this is now going to be the commutator of Lz and L plus or minus acting on f, plus L plus or minus Lz acting on f. And I know what Lz does under these circumstances, since f is hypothetically an eigenstate of the Lz operator. It's just going to give me mu f back. This commutator, I also know how this behaves. This is Lz. In the last lecture, we were able to, purely by examination of the structure of the angular momentum operators, derive the quantization properties of angular momentum in quantum mechanics. We were able to examine the commutators, manipulate the operators, and essentially derive the eigenvalues associated with the operators L squared and L sub z. That's nice, and it's very useful. The eigenstates associated with Hermitian operators in the Hilbert space have nice properties, but we don't actually know what those eigenstates look like. In order to get something easier to visualize, let's consider what the eigenfunctions are, trying to express the angular momentum operators as partial differential equations that we can solve with the techniques that we've been applying earlier in this chapter. The angular momentum operators that we were working with in the last lecture are expressed in Cartesian coordinates. This was very nice because the Cartesian form has this nice symmetry to it, and we could calculate commutators easily. Just by manipulating these, we were able to derive expressions like the eigenfunctions of L squared had this sort of form. H bar squared L plus 1 was our eigenvalue. Likewise, for L sub z, we ended up with eigenvalues of the form m times some constant h bar. The L's that we got had to be half integers, either 0 or 1/2 or 1 or 3/2, etc. And the constants m that we got here had to be between minus L and L, going up in steps of 1. So our eigenvalue structure here, as I mentioned, doesn't tell us anything about the actual form of f. When we were working with the one-dimensional quantum harmonic oscillator, we were able to derive, for instance, the ground state by knowing that the lowering operator acting on the ground state gave us 0. That was a differential equation that we could work with since we knew differential forms for the lowering operator. We can do the same thing with the angular momentum operators, but in this case, it's more worthwhile to think more generally. So suppose we just have some general psi of r, theta, and phi. This is our wave function expressed in general polar coordinates, and it would be nice to know how our angular momentum operators act on this general wave function. if we can express our angular momentum operators in spherical coordinates, we can write down this sort of eigenvalue equation. It will then be a partial differential equation that we can solve, in general, for any value of L or M. Unfortunately, in this lecture, we run into some thorny notational issues. I like to use hats to designate operators. Griffiths, your textbook author, likes to leave the hats off when it's not ambiguous. This is one of those cases where it is ambiguous, and I would like to use the hats, but unfortunately, hats are also significant in other ways. In particular, hats in this section of the textbook mean unit vectors. So I'm going to try and follow Griffith's notation, and I'm going to try and point out where things are operators and where things are unit vectors. But in this case, in this lecture, if I write something like Lx, I mean the operator. And if I write something like r hat, I mean the unit vector. Like I said, I'll try and be clear about what I mean in each case. At any rate, our goal here is to come up with spherical coordinates expressions for the operators that we were working with when we were considering angular momentum operator algebra, L squared and L sub z. So first of all, let's consider just L in spherical coordinates. There's going to be a lot of math in this lecture, and I'm going to go through it only conceptually. The level of grunge in this sort of coordinate transformation is above and beyond what I would expect you to be able to do for an exam. So, most important, I need you to understand the overall structure, the sorts of manipulations that are being done. Change of variables in the context of partial differential equations is tricky, so let's try and just understand overall how it works. First of all, what we're working with is angular momentum, L, which is given by r cross p. Now, I've left both vector hats and operator hats off of these, but this is the angular momentum operator, this is the position operator in spherical coordinates, and this is the momentum operator in spherical coordinates. The momentum operator in spherical coordinates is rather straightforward to write down. We can write it as minus I h bar times this gradient operator, del, which you know as, I'll write it in Cartesian coordinates, x hat times the partial derivative of x plus y hat times the partial derivative with respect to y plus z hat times the partial derivative with respect to z. You can apply this to an arbitrary function of x, y, and z, a scalar function, and it will give you a vector. So this is a vector, as is the momentum, so this is a sort of momentum vector operator. This gradient can be expressed in spherical coordinates as well, and expressed in spherical coordinates, it has this partial derivative with respect to r, partial derivative with respect to theta, and with respect to phi. The partial derivatives with respect to theta and phi have to be rescaled, since, for instance, if you consider it in Cartesian coordinates, this is essentially a spatial rate of change. It's a vector that points in the direction that the function changes most quickly with respect to physical space. And a change with respect to theta is not a change with respect to physical space. R d theta is a motion in space, whereas r sine theta d phi is a motion in space. So these are our motions in space, and the rescaling necessary is taken care of by this 1 over r and this 1 over sine theta. This gradient gives us the momentum, which we can cross with the radius operator, the position operator in spherical coordinates, which is quite simply r hat. So this hat now designates a unit vector, and this designates a coordinate. And as usual, our position operator is multiplication by the coordinate in question of, well, the multiplication of this with whatever the operator is acting on, some function in this case. So our angular momentum then is going to be a cross product of something like, I don't know why I erased it, r hat. So I'm going to be taking the cross product of r hat, that's the vector part of my position operator, with this part of my momentum operator. I can pull my minus I h bar out, and this is what you end up with, simply taking cross products r cross theta, and r cross phi, where here I had a 1 over r in my gradient, but it's been canceled out by the r coordinate multiplication in my position operator. Likewise for phi. There was a 1 over r here as well. This can be simplified slightly. You know that r cross r is going to be 0. The cross product of any vector with itself is going to be 0, since the cross product depends on the angle between the vectors. They have to be pointing in different directions. R cross theta is going to give me phi hat, the unit vector pointing in the phi hat direction. And r cross phi is going to give me minus theta hat, a unit vector pointing in the minus theta direction. You can, therefore, you're only going to end up with two terms, and that will be our angular momentum operator. Since, however, what we were actually doing when we were working with L squared and LZ, we needed expressions, for instance, for things like L plus or minus. This L plus or minus was expressed in terms of Lx and Ly. So what we actually need to do is take the overall angular momentum operator in spherical coordinates and use it to find angular momentum operators in Cartesian coordinates expressed in spherical coordinates. Now this is a very strange way of saying things, but essentially what I want is the angular momentum about the x-axis, the x component of the angular momentum, but expressed still in spherical coordinates. The way to do that, and the way Griffiths uses at least, is to take this expression for the angular momentum operator, which has phi hat and theta hat in it, and express the phi hat and the theta hat in Cartesian coordinates. Those Cartesian coordinates values of theta hat and phi hat will depend on theta and phi, so we end up with this weird hybrid Cartesian spherical coordinate system. But doing so allows you to identify the x component of the angular momentum, y component, and z component. If you actually do that, substitute in phi hat in Cartesian coordinates, for instance. Phi hat in Cartesian coordinates, this weird Cartesian spherical coordinate system, is minus sine phi I hat plus cosine of theta j hat, where I hat and j hat now are Cartesian coordinate unit vectors. This would normally be written as x hat in a normal physics class, but of course we know x hat as the x component position operator, and we can't reuse that notation. You can see why I'm sort of glossing over the details of this. Actually doing it all out would require a fair number of slides and a good deal of your time. At any rate, substituting in this expression, for instance, for phi hat, and a similar expression for theta hat, you can identify the I hat component of L, the x component of the angular momentum. And when you do that, this is what you're left with. So the x component of the angular momentum has derivatives with respect to both theta and phi. Likewise for L sub y, the y component of the angular momentum. L sub z, however, only has derivatives with respect to phi, and this should make a fair amount of sense since z is special in spherical coordinates. Phi is the angle that rotates around the z-axis. So that's all well and good. We're starting to work our way towards expressions of the operators that we're actually interested in, L squared and L sub z. We have one for L sub z, but what about L squared? L squared, it turns out, is easy to express if you think about it in terms of the L plus or minus operators. This was the trick that we used back when we were doing operator algebra. L plus or minus, of course, is expressed in terms of Lx and Ly. But we have Lx and Ly now, so we're ready to go. L plus or minus being expressed in terms of Lx and Ly, going back to your notes from the lecture on the algebraic structure of the angular momentum operators, we can express L squared rather simply in terms of L plus and L minus. L plus and L minus being expressed in terms of Lx and Ly, we can make combinations of Lx and Ly. Multiplying those out is simply exercise in calculus, multivariable calculus, taking partial derivatives, applying chain rules, etc. When you do all of that, evaluating this expression that we got from the algebraic structure of L squared in terms of L plus, L minus, and Lz squared and Lz, you can go and look that up in your notes. You end up with an expression for L squared. This should start looking reasonably familiar. What I really want to do here is write this into an eigenvalue problem by adding some arbitrary function f. This whole operator, acting on some function f, is going to be equal to, we know what the answer is from our consideration of operator algebra. It's going to be h bar squared L plus 1 times f. It's going to give us our original function back. So this right here, this is our partial differential equation that we can solve for f, where f now is a function of r, theta, and phi, and is going to essentially give us our wave function. We only have angular components here, so there isn't going to be any radial part. That should make a good amount of sense. Radial motion doesn't contribute any angular momentum. We can do something very similar for L sub z. L sub z acting on some arbitrary function, and L sub z we already had an expression for. It was minus I h bar partial derivative with respect to phi of f. We know what that's going to give us already as well, because we know the eigenvalue structure of L sub z as well. It's going to give you m times h bar f. Both of these are going to be then partial differential equations that we can solve. This tells us something about the eigenstates of L sub z. This tells you something about the eigenstates of L squared. And if you look at these equations, they should be familiar. These are the angular equations that we had earlier. These essentially gave us the YLM of theta and phi as their solution. So what we've shown here is that the eigenfunctions associated with the L squared and L sub z operators are exactly the spherical harmonics. The spherical harmonics were what we got from a spherically symmetric potential expressing the time-independent Schrödinger equation in spherical coordinates. And this should make a certain amount of sense, since what we're talking about now is angular momentum, and L squared, for instance, angular momentum squared, has to do with the rotational kinetic energy. So it ought to play some role in the time-independent Schrödinger equation, which tells us the energy of the stationary states. So if we have an eigenvalue of L squared, simultaneous eigenstates of L squared and Lz are exactly the spherical harmonics. There is a slight difference here, and it comes down to the value of L. Essentially, we have two classes of solutions here. We have half-integer L and integer L. Our consideration of spherical harmonics gave us only integer L, whereas, our consideration of wave functions, the solutions to these partial differential equations, give us spherical harmonics, which are only meaningful for integer L, integer L. Half-integer L doesn't really make any sense in the context of spherical harmonics, which means if what we're talking about is angular momentum of something like a physical particle, orbital angular momentum, rotational kinetic energy, essentially, we can't have half-integer L. But we do have these half-integer L solutions. If I'm talking about wave functions, I have to have YLMs for my solution. That means I have to have L being 0, 1, 2, etc., and M being, minus L up to L. If what I'm just talking about, though, is the algebra of things, then I don't really know what the solutions look like. But I can have L is 0, or half, or 1, or 3/2. This is interesting. My M values are going to behave the same way, minus L, going up to L. But these half-integer values of L, they're rather strange. They're going to behave in ways that are utterly unfamiliar if what you're used to thinking about are things that actually live in ordinary three-dimensional space. But these do actually happen to have physical reality, and it has to do not so much with orbital angular momentum, the motion of a particle around in an orbit, for instance, as they do with spin angular momentum, or at least that's the name quantum mechanists, I don't think I should say quantum mechanic. Quantum mechanists say is associated with these half-integer values. They have physical meaning in the context of spin angular momentum. As an example of how these angular momentum structures can be useful, consider the rigid rotator. What I mean by that is, suppose I have two masses, both equal to mass m, separated by some distance a. And I put them on a rod of length a, and I spin them around. This is a, system that can in principle be treated with quantum mechanics. The only energy associated with this system is going to come from rotational kinetic energy, since the thing is not allowed to translate. I'm fixing it to rotate about the center here. So my Hamiltonian operator is going to essentially be the rotational kinetic energy, which is going to be L squared over 2 times the moment of inertia. This is the rotational analog of p squared over 2m. I have angular momentum squared divided by twice the moment of inertia, the rotational equivalent of the mass. Now, I suppose I should either erase the hat for my Hamiltonian operator or add a hat to my angular momentum operator. I said in this lecture I wasn't going to use hats to designate operators, so I'll erase it from the Hamiltonian. At any rate, you know how L squared behaves. The moment of inertia here, I, is going to be 2, since I have 2 masses, times mr squared, essentially, so the mass times the radius squared, which is going to be a over 2 squared. So this is going to be ma squared over 2 for my moment of inertia. The time-independent Schrodinger equation then becomes h times my wave function is e times my wave function. That's my original. When I substitute in the specific definition of the Hamiltonian here, I have L squared, my squared angular momentum operator, divided by twice my moment of inertia, which is just ma squared. I have an over 2 here, and I have a 2 here, and they cancel each other out. If this is going to be equal to L squared acting on psi is going to be equal to E times psi, ma squared here is a constant, I can rearrange this and write L squared psi is equal to ma squared E times psi. This now, this ma squared E, this is my eigenvalue of an eigenvalue problem with L squared in it. I know what those eigenvalues are. This is h bar squared L plus 1. That's my eigenvalue, the form of my eigenvalues of the L squared operator. So what that tells me is that ma squared E is equal to h bar squared L plus 1. And I can solve this for E easily. It tells me that E is equal to, an equal sign somewhere, h bar squared L plus 1 divided by ma squared. These are the allowed energies, the energies of the stationary states for the rigid rotator. You can just as easily go through the same sorts of arguments and write down normalized wave functions for the rigid rotator. But essentially this is a very common structure that you're going to encounter in quantum mechanics. Angular momentum is, of course, a conserved quantity in classical physics, and it's a conserved quantity in quantum mechanics as well, which means it's interesting in a lot of respects. And the quantum mechanical structures you get, either if you're looking at something like a rigid rotator now, since we could actually write a real-world wave function for this, we're stuck with just spherical harmonics for the wave functions, integer values for L, and you're going to encounter this sort of expression a lot in quantum mechanics, especially if you go on to the upper levels. Think about for a moment what we've accomplished solely by messing with operators and solving partial differential equations as motivated by this original hypothesis of the time-dependent Schrodinger equation. We were able to determine conserved angular momentum structures. We're even able to predict that there's going to be something strange happening for half-integer values of L in these eigenvalue equations, and that's going to be the topic of the next section in the textbook, spin. The half-integers have a lot of strange properties associated with them. So that's where we are, and that's where we're going. The machinery of quantum mechanics is obviously very productive, and we're going to keep working our way through the results of it for the next couple of lectures. We've spent the last couple of lectures talking about angular momentum. From the quantum mechanics perspective, we ended up talking about a total angular momentum operator, L squared, and a z component of angular momentum operator, L sub z. These two operators gave us a certain algebraic structure, and we ended up with quantum numbers, L and m. The allowed values of L were either integers or half-integers. L could be 0, a half, 1, 3 halves, etc., going up to infinity in steps of a half, whereas m could only be in between minus L and L in steps of 1. These quantum numbers were interesting for a couple of perspectives. If we considered the motion of a particle, for instance, the electron orbiting the nucleus in the hydrogen atom, we only got integer values of L, 0, 1, 2, 3, etc. Whereas the algebraic structure of these operators allows for L equals a half or 3 halves, etc., going up in steps of a half. These half-integer values are essentially valid solutions. And that brings us to the topic of spin in quantum mechanics. Essentially, these half-integer values of L are perfectly valid physical solutions, and they have meaning. They're actually what we use to describe an intrinsic property of fundamental particles like electrons called their spin. Spin is essentially a property of the universe. That's just the way things are. I don't have a good answer for why does an electron have spin, but I can describe the spin of the electron, and I can describe it using the same language as we used when we were discussing angular momentum. So, angular momentum, we were working with equations like L squared F, and the eigenvalues we got for that were h bar squared L plus 1. Likewise, L sub z applied to F gave us eigenvalues of the form m h bar. Examining the algebraic structure of this gave us allowed values for the L quantum number of 0, or a half, or 1, or 3/2, etc. These integer and half-integer values had different interpretations. If I look at just the integer values, those describe orbital angular momentum, the angular momentum of a particle as it moves in a circle around a focus, for instance, around the center. So now we're talking about particle motion. And we can write a wave function, psi, of, say, x, y, and z, or perhaps more accurately, r, theta, and phi, that has this property of orbital angular momentum. You know what the answers for this are already. We've discussed it in previous lectures. The wave functions with specific values of L squared and L sub z, the eigenfunctions of the L squared and L sub z operators, are the spherical harmonics. We're also allowed to have spin, angular momentum, with integer values, but spin is really more interesting when we're talking about the half integers, 1/2, 3/2, 5/2, etc. I keep writing 3/3. I wonder why. Here, these half-integer cases don't have any nice wave function that we can express, so we're really only talking about spin under these circumstances. So, what exactly is this spin thing? I can't give you a good argument or a good answer for this, other than saying this is essentially just a property of the universe. The name spin, at least, I can explain, and the name comes from a classical analogy. Suppose we have a positively charged nucleus and a negatively charged electron orbiting that nucleus. We are going to have orbital angular momentum associated with the motion of that electron, but there's also the possibility that the electron itself would be rotating. We've built up, over the past few chapters, a fairly complete understanding of how single particles behave in quantum mechanics. We can describe them with wave functions like psi of x, y, z, functions of position, which we can use to calculate expected values of, for instance, of what the x-coordinate will be. We know how to calculate the allowed set of energies for bound states, for instance, of the hydrogen atom, and we can predict the spectra. This is very nice and it's very useful, but it's of course not the end of the road for quantum mechanics. The next step that we're going to make is to talk about multiple particle systems, to start building things that are more complicated than a single particle in a single potential. The first step, then, is to expand on our formalism of wave functions to two-particle systems. If we're working with a one-particle wave function, psi, of x, y, and z, if we're working with two particles, we no longer have the position of just one particle, x, y, and z. We're working with two particles, so the wave function psi is going to be a function of 6 variables, x1, y1, z1, and x2, y2, and z2. This means if we construct, for instance, a probability density for finding the particle at a particular position, we're not finding the particle. There are two particles. There are two positions. And what we get is a joint probability distribution for the position of both particles. So this is if we're talking about two particles, and you can easily imagine what would happen if we had more particles. You would have simply more arguments. This is part of what makes quantum mechanics so difficult to compute with, since effectively representing functions of many variables in the computer is a very difficult proposition. If our wave functions are functions of multiple variables, you might expect that our Hamiltonians would get more complicated as well, and they do. The Hamiltonian operator, which we had before, was simply, in the single particle case, was a momentum operator and a potential operator. Now you'll have to deal with the momentum of each particle separately. So for instance, the Hamiltonian for a particle might look like minus h bar squared over 2m times, and I'll write this as gradient squared with a subscript 1 minus h bar squared over 2m gradient squared with a subscript 2, where the gradient with a subscript 1 refers to partial derivatives with respect to x1, y1, and z1, and the subscript 2 refers to partial derivatives with respect to x2, y2, and z2. Essentially, this is the momentum of particle 1 in operator formalism with wave functions, and this is the momentum of particle 2. The potential energy now, of course, will also have to be a function of the positions of both of these particles, so we'll have to add on a potential term which is a function of both r1 vector and r2 vector. There are some simplifications that you can make. If the potential is only a function of the separation of the particles, for instance, you can do the same sort of thing as you can do in the case of the two-body problem in classical physics. Namely, instead of working with two independent bodies, work with the center of mass and the essentially angular orientation of the bodies about the center of mass. But that's a story for another day. The Hamiltonian we get here is now a partial differential equation in multiple variables, many more variables than we were working with originally. So it's much harder to work with. Our wave functions, of course, still have to be normalized, since we still have to represent, well, probability densities with them. But the normalizations we're going to work with are a little different. In particular, while the probability density that we're working with is still going to be psi star psi, we're going to have to integrate it over many, many dimensions. 6 dimensions in this case if I'm working with two particles in 3 dimensions, dx1, dy1, dz1, dx2, dy2, dz2. So if you're trying to normalize a wave function for two particles in 3 dimensions in Cartesian coordinates, you've got a lot of integrating to do. The time-independent Schrödinger equation is going to look very similar. Essentially, h psi equals e psi, same as before, where the Hamiltonian now as an operator h hat. The solutions you get to the time-independent Schrödinger equation are still going to behave the same way they behaved before, and this is the very comforting thing. When we derive the time-independent Schrödinger equation from the time-dependent Schrödinger equation, we still get the same sort of behavior. Our wave function now is a function of the positions of two particles, if I represent them as vectors r1 and r2, as the spatial part, the solution to the time-independent Schrödinger equation, and the time dependence looks very much the same, minus I e t over h bar, the same sort of expression as we got before. So adding multiple particles adds a great deal of complexity to the spatial part of the wave function, but if we have a stationary state, the temporal evolution is as simple as it was before. The subtle point of multiple particle wave functions comes from whether the particles are distinguishable or indistinguishable. Consider combining two one-dimensional systems. So the position of particle 1 is represented by x1, position of particle 2 represented by x2. So we have two particles in a one-dimensional system essentially, and the positions of those particles are independent. This looks a lot like two independent variables. So you can think about this as, in 2 dimensions, an x1 axis and an x2 axis. If I measure the positions of these particles at the same time, I illuminate the system with high energy radiation and look for where the radiation has scattered off of the positions of the particles. I can represent the outcome of a measurement by a point in this 2-dimensional space. Suppose this point is 1, 0.3. I might also measure the particles to be here. Another possible outcome for this measurement is 0.3, 1. What I mean by whether the particles are indistinguishable or distinguishable is whether these two outcomes, 0.31 or 1, 0.3, are actually distinct. If I was measuring this in a 2-dimensional space, these points would, of course, be very distinct. But I don't actually have a 2-dimensional space. I have a 1-dimensional space with two particles in it. So if I measure, say, this outcome in 1-dimensional space, I'm measuring one particle at point 0.3 and another particle at position 1. So my wave function then essentially has a particle there and a particle there. If I measure this other outcome, 1, 0.3, one of my particles is at position 1, one of my particles is at position 0.3, so my wave function essentially looks like that. These guys are essentially the same. What does that mean? Well, if this is particle A and this is particle B, and this is particle A and this is particle B, then these two outcomes are different. But that requires the particles themselves to be distinguishable. And if the particles are not distinguishable, if this is an electron and this is an electron, there is no difference in principle between the electrons in these two peaks, then, well, electron-electron and electron-electron are actually the same outcome. And whether or not you count these as different is, well, one of the nuances of quantum mechanics. The essential fact that you have to keep in mind is that in quantum mechanics, the particles that we're working with, electrons, protons, photons, whatever they may be, are in principle indistinguishable. The wave function, quantum mechanics tells us, is all we can in principle know about these particles. So you can't paint one of them red or put a little piece of tape on it or do whatever you might do with other objects in order to keep track of whether or not they've exchanged places, for example. Particles are indistinguishable. Indistinguishable is a painfully long word, but essentially what this means is that we can't tell which particle is which. So let's consider what effect this has on quantum mechanics. If you had particles that were distinguishable, particle 1, its position being represented by the coordinate x1, could be in some wave function, in some state, psi sub a. And this would be quantum mechanically a complete description, all of the information necessary about particle 1. Likewise for particle 2, indexed by coordinate x2, in state psi sub b. The combined wave function for the overall state, then, is going to be psi as a function of x1 and x2. And we can write that down if particle 1 is in state psi a and particle 2 is in state psi b as simply the product psi a of x1 times psi b of x2. This gives us the sort of expression that you would expect to get for distinguishable particles. Namely, for instance, if I want to calculate the expected value of x1 for a particle in this state, this is the expected position of particle 1. My combined wave function here, calculating the expected value in this combined wave function, will require two integrals, one dx1 and one integral dx2. Both integrals are going to go from minus infinity to infinity. And the integrand, as before, is going to be psi star psi. If I expand that out, psi a star of x1, psi b star of x2, x1, and psi a x1, psi b of x2. This is the integrand you would get. Psi star and psi combined together with a multiplication means that's our probability density for position, and this is then, of course, the expected value of position formula that we're familiar with from single particle quantum mechanics. Looking at what's a function of what here, we can simplify things a little bit. I have functions of x1, and I have functions of x2. If I pull the terms that are not functions of x2 out of the x2 integral, essentially moving them over here, what I end up with is two integrals that you probably recognize. Integral from minus infinity to infinity dx1 of psi sub a star of x1, x1, psi sub a of x1 for my first integral, and the integral from minus infinity to infinity of, with respect to x2, of psi b star of x2, psi b of x2. So these integrals essentially separate out, and this is a normalization integral for psi sub b. If psi sub b is normalized, this is going to go to 1. And this expression on the left, the integral with respect to x1, is the single particle expectation value of the position x1 for a particle in the state A. So essentially, if I have distinguishable particles, my result looks pretty much as expected. These particles are clearly distinguishable because if the expected value of the position of the particle were different for state B as for state A, well, I got the expected value for state A, not some combination involving the expected value for state B. So these particles are clearly distinguishable, and there's nothing in principle wrong with writing wave functions like this, except for the fact that the fundamental particles we're working with are not distinguishable. So we have to somehow encode the indistinguishability of particles into our formulation of quantum mechanics. So how do we write a wave function for indistinguishable particles? The key fact is what happens if we exchange the particles. The wave function for particle 1, particle 2 versus the wave function for particle 2, particle 1. Exchanging the positions at which we evaluate coordinates is essentially, if you think back to that plot I was making earlier of x1 and x2, it's implying a degree of symmetry between this point and this point. That my wave function must be equal here and here, essentially being equal somehow across the axis. This sort of line here where x1 equals x2. That degree of symmetry implies some constraints on allowable forms of the wave function. We don't need just that the wave function itself doesn't change if I exchange x1 and x2. What we need is for the observables not to change. And furthermore, we need the observables not to change at all if we swap the particles back to where they were originally. So if we want the exchange of particles to not matter, let's define an exchange operator, p hat. Now don't worry, we're not going to be working with p hat in the context of it as a mathematical operator, but it's a useful notation to use. What we need in order for the wave function essentially to not change the observables is for p hat acting on psi, x1, x2, which is more or less defined to be psi of x2, x1. We need that to be equal to plus or minus psi of x1, x2. You know the way to not change the observables in quantum mechanics is to multiply by a complex phase, and this plus or minus essentially takes care of that complex phase. You could imagine any arbitrary e to the I phi being multiplied by psi, and that would not change the observables, but the fact that applying the exchange operator twice gets us back where we started means that the phase that we multiply by has to be either 0 or pi, meaning we have to either go from plus psi to minus psi or from plus psi to plus psi. Either we don't change the wave function at all by exchanging operands, or we flip the sign of the wave function by exchanging the particles. This is sort of a law of physics. The indistinguishability of particles requires this to hold. If I exchange the order of the arguments of a two-particle wave function, I must get my original wave function back with a plus or a minus sign. This symmetrization or anti-symmetrization under exchanging the arguments, it's symmetry referring to the plus sign, anti-symmetry referring to the minus sign, has some remarkable consequences, which we'll talk about over the next couple of lectures. One way, however, to write down these wave functions, since that's what we're going to want to do in the end, is if I have the two single particle states that I was working with in the past slide, psi A, psi B. My wave function, psi of x1, x2, started off as psi sub A of x1, psi sub B of x2. This was the distinguishable particle wave function, and it turns out that if I combine this with a permutation of x1 and x2, for instance, psi A of x2 instead of psi A of x1, and then psi B of x1 instead of x2, if I combine these two pieces with either a plus sign or a minus sign, I get something that obeys the requirement that the particles are indistinguishable from the perspective of quantum mechanics. If I'm going to properly normalize this, I'll need a normalization constant out front. And for instance, you can check this fairly easily. If I wanted to know what psi of x2, x1 was here, well, it's going to be this expression on the right, exchanging 2's for 1's and 1's for 2's. So it's going to give me A, psi A of x2, psi B of x1, plus or minus psi A of x1, psi B of x2. If you compare the expression I get after exchanging these particles with the expression I got before exchanging these particles, you can see here's psi A x1, psi B x2, A1, B2, whereas here's A2, B1, A2, B1. So these expressions are essentially the same, except the plus or minus sign is going to mess things up a little bit. If I use the plus sign, clearly these two expressions are the same. A1, B2 plus A2, B1 versus A2, B1 plus A1, B2. All I've done is exchange the order of these two terms. Since this is just multiplication, we're working with wave functions, there's nothing fancy about the order of the terms over addition. Everything commutes, that's fine. If I use the minus sign, I have A1, B2 and minus A1, B2 in my exchanged version, whereas minus a2b1 becomes plus a2b1 in my exchanged version. So I flip the signs in my wave function if I use the minus sign when I calculate my exchanged form. So this trick for making indistinguishable particle wave functions from distinguishable particle wave functions actually always works. You need to combine all of the different permutations of all of your particles with appropriate plus or minus signs such that you obey this overall anti-symmetry under exchange or symmetry under exchange requirement. Whether or not we have symmetry or anti-symmetry under exchange is a really interesting topic. And it gets us down to a distinction that I've mentioned earlier on in the context of fermions and bosons. Essentially, indistinguishability has a couple of consequences. First of all, if I have the plus version, the symmetry under exchange, essentially psi of x2, x1 equals psi of x1, x2, my exchanged version is equal to my original version. This is the case for bosons. And bosons were the particles that we talked about earlier that had spin, integer spin, 0, 1, or 2, etc. If you make the other choice, say psi of x2, x1 is equal to minus psi of x1, x2, that's the case for fermions. And fermions, we said earlier, were particles with half integer spin. Spin 1/2, 3/2, 5/2, etc., on up to infinity. There's actually quite a lot that you can do with this. For instance, the symmetry and anti-symmetry properties of these wave functions have, well, it has observable effects, and the behavior of fermions and bosons is crucially different in a lot of ways that have very important consequences. For instance, earlier on we talked a little bit about superfluid helium in the context of the domain of quantum mechanics and whether that was important or not. Helium atoms are bosons with integer spin, and they have very different behavior than other liquid gases, for instance. If you wanted to determine the quantum mechanical behavior of very cold liquid hydrogen, for instance, it would behave differently. Hydrogen behaves differently from helium in that context. The indistinguishability of particles is something of an axiom in quantum mechanics. The exchange can't affect anything. In particular, it doesn't affect the Hamiltonian. Exchanging two particles should not affect the energy of the state if the particles are completely indistinguishable. Put another way, the exchange operator and the Hamiltonian operator commute. The commutator of p hat and h hat is 0. What that means is that we can always write wave functions in these forms. x2, x1 after exchange equal to plus or minus psi of x1, x2. We can do that and still be able to come up with stationary states. We can come up with a simultaneous set of eigenstates, a set of simultaneous eigenstates of both this exchange operator and the Hamiltonian. So it's always possible to write our wave functions like this. This is similar to the reasoning we applied earlier when we were talking about functions, or about the time-independent Schrodinger equation in one dimension with an even potential. You could always write the solution as either even or odd if the potential is even in one dimension. You can make a similar argument, or this is a very similar argument. There is a symmetry property that we can exploit when we're looking for solutions of multiple particle wave functions. So bosons and fermions and exchange, these are fundamental properties of nature, and the connection between the spin of the particle and the symmetry or anti-symmetry of the wave function overall is a really interesting topic that we'll discuss a little more later on. One application that you guys have hopefully heard about from your chemistry class is the Pauli exclusion principle. The Pauli exclusion principle holds for fermions, and for fermions we know that the exchange operator acting on the wave function psi gives you minus the wave function psi. So suppose the wave function that we were working with was writable in the form that we were talking about earlier. Psi of x1, x2 is equal to some normalization constant times psi a, x1, psi b, x2. Now we're using the minus sign since we're talking about fermions. We're talking about exchange antisymmetric spatial wave functions. Psi a, x2, psi b, x1 for our second term as before. The Pauli exclusion principle determines what happens if the two particles are in the same state. If the two particles are in the same state, psi a is equal to psi b. What that means is that I can rewrite this as psi a and rewrite this as psi a. You can tell what we're left with now. We've got psi a x1, psi a x2 minus psi a x2, psi a x1. We've got essentially something minus itself. So if the particles are in the same state, then psi of x1, x2 equals 0 with this particular fermion antisymmetry under exchange. This is interesting, and I suppose I shouldn't use an exclamation point here because 0 factorial is 1, and that wouldn't be all that interesting. But what this means is that this is not possible. First of all, the wave function psi equals 0 is a perfectly valid solution to the Schrödinger equation, but it doesn't tell you anything, so this is not useful. It does not describe a normalizable state. What this means, and what the Pauli exclusion principle says, is that two fermions cannot occupy the same state. I'm not quite sure how I spelled occupy there, but I don't think it was right. Two fermions cannot occupy the same quantum mechanical state, and that comes from the fact that fermions are required to obey antisymmetry under exchange. And of course, if you have two particles in the same state, exchanging things doesn't do anything. It's not going to change your wave function. So if it's not going to change your wave function, and yet it is going to change your wave function by giving it a minus sign, you've got a problem. Two fermions cannot occupy the same quantum mechanical state as a result. And this comes just from the nature of indistinguishable particles. The antisymmetric combination to render two otherwise distinguishable particles indistinguishable means that those two particles cannot occupy the same state. For bosons, though, we use the plus sign, so that's no problem. If we use a plus sign here, we end up with psi a x1, psi a x2 plus psi a x2, psi a x1. So just twice psi a x1, psi b x2. Psi a x2. So that's a perfectly valid wave function. Bosons, if we use the plus sign, make the symmetric instead of antisymmetric combination to render the particles indistinguishable. Those particles can occupy the same state right off the bat. This ability to put multiple particles into the same quantum mechanical state is the difference between the bizarre behavior of liquid helium and the behavior of liquid hydrogen. As an example, consider back to the very beginning. The very first quantum mechanical system we worked with was a particle in a box. What happens if we put two particles in a box? Well, two particles in a box, if we're going to write wave functions as symmetric or antisymmetric combinations of our distinguishable single particle wave functions, is a little bit of a lie. Because if these particles are anything that we know of realistically, those particles will interact, and the interaction in the Hamiltonian will affect the potential. So we won't be working with a simple v of x equals 0 inside the box and infinity outside the box potential. We'll be working with something more complicated, and accounting for that interaction will mean that our stationary states are not simply the stationary states of single particles. But suppose, for instance, vigorously waving my hands, though you can't really see it in a video lecture, suppose those particles didn't actually interact, then the potential would not be affected and the stationary states would indeed be the single particle stationary states. If I have distinguishable particles then, I can write down my states as, for instance, psi nm of x1, x2 as, well, the product of the state for n and the state for m. Psi sub n of x1, psi sub m of x2. The ground state, for instance, and I'm going to smush this down, give myself some space. The ground state then has n and m both equal to 1. In this case, looks like my normalization overall out front, 2 over a, different normalization since I've got the product of two separately normalized functions, times sine of pi x1 over a, sine of pi x2 over a. And it has energy, if I substitute 1 for the energy of one particle and 1 for the energy of the other particle, I'm just going to get k plus k. My total energy is 2k. The first excited state, and there are two ways I can do this. I could write psi 2,1 or psi 1,2, depending on which particle I bump up from the ground state, is going to be very similar. It's going to be 2 over a sine pi x1 over a sine 2 pi x2 over a, if, for instance, I use this combination. So there are actually two distinct ways to write the first excited state. One where I put the 2 with the x1, and the other where I put the 2 with the x2. That means this first excited state, for this distinguishable particles case, is doubly degenerate. There are two allowable states with the same energy. That's what we mean when we say degeneracy. Suppose instead of distinguishable particles, I had bosons. The states that I would work with then would look very similar. If I had psi 1,1, my ground state, well, there's nothing wrong with putting two quantum mechanical particles in the same quantum state with bosons. So I'd have to make the symmetric indistinguishabilization. Sure, why not? I'll make up a word. The symmetric form of this, sine of pi x1, sine of pi x2, plus sine of pi x2, sine of pi x1, but since they're the same, that's all just going to end up adding up. So your ground state is essentially going to be unchanged from your distinguishable particle case. If your distinguishable particles are in the same quantum state, are they really all that distinguishable? So psi 1,1 is unchanged. The first excited state, however, that looks a little different. Psi 1,2, for instance. Let me actually not write it as psi 1,2. Let me write it as psi first excited. And that's going to be a symmetric under exchange version of the distinguishable particle wave function here, such that the particles are rendered indistinguishable. What it ends up looking like is root 2 over a times sine of pi x1 over a sine 2 pi x2 over a plus sine 2 pi x1 over a sine pi x2 over a. So I've moved the 2 from the term with x2 to the term with x1. And if you calculate observables with this first excited state, you'll get a different result than if you had two distinguishable particles. For instance, if I calculate the expected position of particle 1 or particle 2, I'll get the same answer, which is a requirement if the particles are going to be distinguishable. One thing to notice about this is that if I try to swap which of x1 or x2 has the 2, it doesn't work. I get the same quantum mechanical state back. So this is non-degenerate. There is only one allowed quantum mechanical state for the first excited state for bosons. Degeneracy does have consequences in the physical world. So the fact that distinguishable particles and non-distinguishable particles have different degeneracies for the first excited state means that, well, it means we're onto something. There should be some observable consequences for this prediction. The last possibility, fermions. Well, what about the ground state, psi 1,1? The Pauli exclusion principle tells us that no two fermions can occupy the same quantum mechanical state. And in fact, if you look at our psi 1,1 state here, and try to make a antisymmetric under interchange version of it by adding on essentially another term that looks exactly like this, or more accurately, subtracting off a term that looks exactly like this, you get 0. So the ground state doesn't exist. There's no psi 1, 1 under these circumstances. Our new ground state, then, is essentially our first excited state from before, but with a minus sign. And I'll indulge in a little copy pasting here, just to save myself the writing. The only difference here is that we have a minus sign to render the two states antisymmetric under exchange, and we're combining two terms such that the resulting state is a valid state for indistinguishable particles. So our ground state again, which corresponded to our first excited state before, is also non-degenerate. There's only one allowable state here for our ground state, only one quantum mechanical state. And, well, fermions, bosons, and distinguishable particles obviously behave very differently here. Fermions and bosons differ in the sense that the ground state is different. Indistinguishable particles and distinguishable particles differ in the sense of the degeneracy of whether or not of the states. So there's a lot of interesting phenomena here, and it all boils down to this fundamental fact that quantum mechanical particles are indistinguishable. There is no difference between two electrons. Any two electrons are essentially exactly the same. They obey the same laws of physics. There is no additional information here that would allow us to keep track of which electron is which. We can make quantum mechanics validate this approach, we make quantum mechanics fail to keep track of which particle is which by making these symmetric or antisymmetric combinations of what would otherwise be distinguishable particle wave functions, and lo and behold, the distinguishable particles, bosons and fermions, all behave differently. So there's a lot going on here. To check your understanding, just to drive home the complexity of multiparticle wave functions, I'd like you to write down the normalization integral for a 3-particle wave function in 3-dimensional space. Finally, reflect on what it means for two fermions to be non-interacting if they can't occupy the same quantum mechanical state. Those two particles in a box that I did on the last slide, for a fermion, they couldn't exist in the same state, but I wrote down the ground state. I wrote down the stationary states from which I was constructing those antisymmetric and symmetric combinations by stating that the particles didn't interact. So what does it mean for two things that don't interact to exclude each other from doing something? And finally, what I've been talking about in the context of the particle in a box is just the spatial wave function. We're just talking about psi of x, for instance, or in the case of two particles, psi of x1, x2. How would that change if I included spin? Particle 1 and particle 2 will now have independent spins, which you can think of as extra arguments to your wave function. So how might the inclusion of spin affect this symmetrization or anti-symmetrization? These are things to reflect on. And if you've got these down, I think you've got the basics of multiparticle quantum mechanics soundly in your mind. Quantum mechanical systems with many particles in them are very difficult to solve in principle. Imagine trying to write down the wave function for a system of 10 to the 23rd, not quite independent particles. That would be very, very complicated. And under most circumstances, the best that we can hope for is to uncover the general structure of the solution. What sort of energies are going to be allowed, for example. What we're getting into now is the basics of the quantum mechanical structure of solids, which is of course an incredibly rich subject, being, as it is, essentially the basis for all of materials science, all of semiconductor physics. One aspect of the theory of solids that we can actually do reasonably accurately, at least from a qualitative perspective, is the behavior of free electrons in conductors, and that's the topic of this lecture. Free electrons in a conductor are something that we can work with reasonably well, because if we think about a chunk of material, for instance, as being the space over which some electron, a conduction electron, is free to wander, the particles are essentially free. The electrons, however, will never be found outside the box, or outside the material. It's very unlikely for an electron to wander off into the air surrounding a chunk of conductor. Conductors just don't do that. So the particles are not found outside the box. The electrons are confined. You can probably see what I'm getting at here. We have free particles that are never going to be found outside of some rectangular region. This is starting to look like the particle in a box. So maybe we can work with that. What about a particle in a box? Well, a single particle in a box, that's easy enough to handle. But what about multiple particles in a box? What if I have a second particle here that's also wandering around on its own? Well, provided I make the very, very inaccurate yet useful assumption that these particles don't interact much, I can actually work with that. Now I'll put a star on that, sort of a footnote, asterisk, because this is not a very good assumption that the electrons in a metal don't interact. Essentially what this assumption amounts to is that, on average, particles aren't going to interact much. Two randomly chosen electrons in a metal are unlikely to have just recently collided, for example, and that, on average, the vast sea of electrons that are not free to move about this equalize the charges to the degree that any two conduction electrons are unlikely to encounter the free charges of either the nucleus, free charges of the other electrons, or free charges of other conduction electrons. Those are some pretty stiff assumptions, and they're probably not correct. But if we make those assumptions, we can actually solve this problem and figure out what the quantum mechanical structure is. That's a very useful thing to do, so we're going to go ahead and do it. The starting point, though, is a single particle in a box. The single particle in a box in 3 dimensions is something that we've talked about, and the Hamiltonian that we're working with is essentially just given by the momentum squared, the kinetic energy, h bar squared over 2m times the gradient operator in 3 dimensions. We also have to multiply by a potential, which is now going to be a function of x, y, and z, where the potential we're working with, v of x, y, and z now, is equal to, well, 0 if we're inside the box, and that's going to happen for x, y, and z in between, let's say, L sub x, L sub y, and L sub z, and 0, respectively. So if x is between 0 and Lx, y is between 0 and Ly, and z is between 0 and Lz, the particle is officially in the box, and the potential energy function is 0. We say the potential energy is infinity outside the box to enforce the particle to always be inside the box. This is essentially identical to our one-dimensional particle in a box. We just have more dimensions to work with, and the solution procedure is very similar. The Schrodinger equation we're working with is, as usual, the time-independent Schrodinger equation, h psi equals E psi, and if we make our usual separation of variables assumption that psi is given by some function of x multiplied by some function of y multiplied by some function of z, what you end up with is 3 separate, independent, one-dimensional particles in a box, infinite square well potentials, essentially. One in the x direction, one in the y direction, and one in the z direction. The overall energy of your combination after you've done separation of variables is given by essentially the energy contributed by the x, and the energy contributed by the y, and the energy contributed by the z, independent, one-dimensional particles in a box. The wave functions that you get, psi of x, y, and z, are products, then, of 3 one-dimensional particles in a box. The normalization you get is 8 divided by Lx, Ly, Lz in a square root sign, and then you have your sine functions, as usual for the 1D particle in a box. Sine of nx pi x over Lx, where the quantum number that you get as a result of the boundary conditions, I'm calling nx for the x part, ny for the y part, and nz for the z part. Ny pi y over Ly, sine of nz pi z over Lz. That's your wave function for a single particle in a 3-dimensional box. The general solution you get in separation of variables, as usual, has sine and cosine terms in it, but the boundary conditions not only fix our quantization, give us quantum numbers nx, ny, and nz, but also eliminate the cosine terms, just because the wave function must go to 0 at points where the potential diverges to infinity. The Quantization also sets the allowed energies of the system, and the energy of this state is given by h bar squared pi squared over 2m, and then we have a combination involving these quantum numbers, nx squared over lx squared plus ny squared over ly squared plus nz squared over lz squared. Now this looks like a sum of three things squared, and it's useful to make this look more like the magnitude of a vector in 3 dimensions. Essentially, I'm going to define a vector, or a scalar quantity, for instance, k squared, a k vector, such that this overall energy here is equal to h bar squared k squared over 2m, looking like the kinetic energy of a particle with wave vector k being essentially 2 pi divided by the wavelength. The k vector that we're working with then is, for instance, given by kx is equal to pi nx over lx. Likewise, for ky equals pi ny over ly, and kz is equal to pi nz over lz, where the overall k squared is kx squared plus ky squared plus kz squared. If I make these definitions, the overall energy now starts to look like the squared magnitude of a vector in a three-dimensional space with three separate components, kx, ky, and kz. And this k space, three-dimensional space, is the space that you want to think about in terms of the quantum mechanical structure of many particles in a 3D box, which is, of course, where we're going with this. So what happens when we have many particles in a box? Well, we know we're working with fermions here, and fermions obey the Pauli exclusion principle, which means we're not going to be able to put more than 2 fermions in exactly the same quantum state. So if I'm trying to occupy many states here, I'm going to need many states to be, well, I'm going to need to understand the structure of many states. So thinking about this in terms of the three-dimensional k vectors, say this is my kx direction, this is my ky direction, and this is my kz direction. The overall allowed values that I had for my energy were given by specific integers, essentially dividing these k axes up into specific points. Kx was defined by pi nx over lx, for instance. So nx being 1, 2, 3, etc., like for our one-dimensional particle in a box, I essentially have a set of ticks along my x-axis here, my kx axis, that tell me what the allowed values of kx are. Likewise, I have a set of allowed values for ky, and a set of allowed values for kz. And it's going to be hard for me to draw this out in 3 dimensions, but if you think about the allowed values, where these things all intersect, when I have an allowed value of kx, an allowed value of ky, and an allowed value of kz, I have an intersection point there. That means I have an allowed quantum state here for nx is 1, ny is 1, and nz is 1. I, of course, also have an allowed quantum state out here, where nx is 2, ny is 1, and nz is 1. And I'm not doing a very good job drawing this, but you can see each intersection point here is associated with some cube between the intersection and the origin. And that cube signifies a certain volume. And the volumes in K-space are something that's very useful to think about. So this point now here would represent ky is 2, kz is 1, kx is 1. Each of these points is associated with a cube. And the volume of this cube, which is going to become important when we start talking about trying to fill as many of these states as possible, is given by, well, the length of each of these sides. I'm talking about the volume in K-space now. This, of course, being associated with nx equals 1, this is pi divided by lx, is the length of this side in K-space. Likewise, this is going to be pi over lz. The y, of course, is going to be pi divided by ly. So if I wanted to know the volume of one of these cubes in K-space, it would be... You saw in the last lecture how just considering the electrons in a conductor to be free particles in a box, you could get a reasonable impression of the quantum mechanical behavior of those electrons, what the allowed energies look like, what the behavior of the metal was even to some degree. We were able to calculate, for instance, the degeneracy pressure of the electrons in that state and get an answer that was comparable to the measurable physical properties like the bulk modulus of the material. That free particle assumption seems very fishy, though, because those conduction electrons are going to interact with the atoms in some way. So what I'd like to talk about in this lecture is how we can include the atoms and the results, in particular the band structure of energy levels in solids. Including the atoms in the behavior of the free electrons in a material, for instance, is a rather complicated process. You might think about an electron coming in towards some atom, where we have electrons orbiting the nucleus of the atom, and how these particles might interact. Now, we know from quantum mechanics that this picture is just plain not correct, that we need to consider the electron as it approaches the atom as some sort of a wave packet. So I'll draw some wave fronts. And the atom itself as being composed of a nucleus, which has almost negligible wave nature compared to the wave nature of the electron, since the nucleus is so much heavier, surrounded by some cloud of electrons. Describing the interaction of a wave packet like this and an atom with an electron cloud surrounding it is a very complicated process in principle. But whatever the interaction is, it's going to be encoded by some Hamiltonian, h hat, which is going to include the kinetic energies of the particles and then some potential that tells you how the energy of this interaction takes place. If the electron were very close to the atom, would there be an attractive force? Would there be a repulsive force? Would there be an increase in energy or a decrease of energy? Now, typically you can assume that the potentials like this are related just to the relative displacement between the atom and the electron, so some difference between the position of the electron and the position of the atom. Perhaps the potential even only depends on the absolute magnitude of that vector, only depending on the distance between the electron and the atom. Either way, these potentials can come in a variety of forms. But if you're trying to consider a material with many electrons and many atoms, what you're going to have to work with is actually going to be a sum over all the atoms of the material of the contribution of each atom to the energy of an electron. If we have multiple electrons, we'll have to have lots of different kinetic energy terms, and we'll have to have a sum over electrons here as well. So this is a very complicated Hamiltonian. We can't really hope to solve it analytically. We can, however, make some analytical progress if we make some simplifications. And I'm going to make 3 simplifications for this lecture. First of all, this potential, which is in principle a function of the distance between the electron, the position of the electron and the position of the atom, I'm going to pretend it only depends on the magnitude of the distance, and I'm going to make a very crude approximation to this potential, namely that if the electron is right on top of the atom, it experiences a very strong repulsive force. If the electron is displaced from the atom significantly, the atom overall looks neutral, and there is no energy associated with that reaction. The approximation I'm actually going to make then is that the potential contribution of a single atom to an electron is given by a Dirac delta function. Some proportionality constant describing the strength of the delta function times the delta function itself as the distance between the electron and the atom. So this is the potential that we're going to work with. This is just for an interaction between a single electron and a single atom, however, and we're going to have to consider multiple atoms. And in order to make any mathematical progress, we're going to have to know the positions of all the atoms. In any realistic material, the atoms will be more or less randomly distributed, though there may be some overall structure dictated by the structure of the bonds between those atoms. I'm going to assume a very, very simple structure here. I'm going to assume that we're working with a crystal. So we're working with a regular array of atoms, for example. Furthermore, I don't really want to mess with trying to express this regular array of atoms in 3 dimensions. So I'm going to assume that we're only working with a one-dimensional system. Essentially a one-dimensional crystal, just looking at a slice through a potential 3-dimensional crystal. This is not the most relevant physical scenario, since a Dirac delta function in 1 dimension extrapolated to 3 dimensions is sort of a sheet delta function, not an array of point delta functions like a crystal. So this is not the most
realistic scenario, but it does actually reproduce a lot of the observed behavior of, well, real electrons in real crystals. The potential we're talking about here, then, is going to be a one-dimensional array of delta functions. So our v of x is going to look something like this. It's going to be 0 whenever you're not on top of an atom, and it's going to spike up whenever you are on top of an atom. And this is going to continue, potentially infinitely, in both directions. This is called a Dirac comb, since I guess it kind of looks like a comb, and it's made of Dirac delta functions. So this is the potential we're going to work with. The nice feature of this potential is that if these atoms are, say, spaced by some distance a, this is a periodic potential, and there are theorems that help us deal with periodic potentials. One of these theorems is called Bloch's theorem, and what it states is that for a potential that's periodic, namely the potential evaluated at some displacement a from the current position is just equal to the potential at the current position, the solution to the time-independent Schrödinger equation for that potential can be written as follows. Psi of x plus a, displacing the argument of psi, is essentially the psi at the current location multiplied by some complex constant with magnitude 1, e to the I k a, for some unknown constant k. Essentially what this means is that the observables don't change. You know, multiplying the wave function by some complex number isn't going to, some complex phase, e to the I k a, isn't going to change the answer. Well, essentially what this means is that for a completely periodic potential, the observables aren't going to change from one period to the next. And that's more or less a requirement. Periodic potentials should have periodic solutions to the Schrödinger equation. We don't know anything necessarily about this constant k, but essentially what we're talking about, if we apply this to our delta function potential, or our Dirac comb potential, is atoms spaced apart by some distance a, and Bloch's theorem tells us that the wave function here gives us the wave function here, gives us the wave function here, gives us the wave function here. So we don't need to worry about the entire space. We can only worry about a sub-portion of the space. This is very useful. One unfortunate consequence of Bloch's theorem is that it only works for completely periodic potentials. So if we're talking about a material, a chunk of silicon, say, there are edges. In the inside here, we definitely have a periodic potential. We have a silicon crystal, we have an array of atoms, that's fine. We're working with something periodic. But at the edges, we're going to have problems. Since at the edges, well, the periodicity obviously breaks down. Under these circumstances, then, Bloch's theorem isn't going to apply. So we need to find out some approximation, some simplification, or at least some plausibility argument for how we can still apply Bloch's theorem to these cases. Well, we've already made a lot of simplifying assumptions, so what's one more? Our potential v of x is this Dirac comb structure that potentially continues to infinity. If we're working with a realistic material, we're going to have something like 10 to the 23 atoms here. As such, the contribution of the atoms you would expect, if you had a free electron here, it's going to be much, much, much more sensitive to the atoms nearby than to the boundaries of the material. As such, you wouldn't expect the edge effects to be terribly significant. So, one way to fix Bloch's theorem, if we're willing to ignore the edge effects and deal just with electrons near the interior of the material, is to take our delta function potential and wrap it around. Essentially treat this edge of the material as connected somehow through a wormhole to this edge of the material, wrapping the material around in a circle, for instance, working with a donut of material instead of a block of material. What this periodicity means, that we're assuming the potential is periodic overall, not just periodic from one atom to the next, is that our wave function psi of n times a, essentially the wave function on the right edge of our material, has to be equal to the wave function on our left edge of the material. And let me rewrite this. I have my wave function as a function of x, and if I add n times a, where I have n atoms from one side of the material to the other side of the material, times the separation of the atoms, I've essentially wrapped all the way around and gotten back where I started. That has to give me my original wave function back. So that's my periodicity. And under these circumstances, Bloch's theorem, which tells me how to displace my wave function by a certain amount, tells me what I need to know. Bloch's theorem gives us that psi of x plus NA is going to be equal to e to the I capital N capital Ka times my original wave function, psi of x. My periodicity then means this is going to be equal to psi of x, which I can just cancel out then from this periodicity equation, giving me e to the I n capital Ka equals 1. That tells me that this capital K constant I have can only take on specific values. And those specific values are given by what will make the exponential 1, essentially 2 pi times an integer divided by capital NA. The argument here has to be 2 pi times an integer, and this is then the value of k that's going to give you 2 pi times an integer when you multiply it by n times a, essentially. So n now is going to be some integer, either 0, plus or minus 1, plus or minus 2, etc. Knowing something about this constant tells us how the wave function in one region relates to the wave function in the next region, and we have a variety of allowed values for this overall constant. So we have now what we need to solve the time-independent Schrödinger equation. The potential we're working with, and I'll just draw a chunk of it here, just with, say, 2 spikes. Let's say this is the spike at x equals 0, and this is the spike at x equals a. I'll add another spike here on the left at x equals minus a. We need to go through our usual machinery for solving the time-independent Schrödinger equation. We have our potential, and in regions, say, there, the potential v of x is equal to 0, which means our time-independent Schrödinger equation is just going to be the free particle equation, minus h bar squared over 2m times the second derivative of psi with respect to x is equal to e times psi. You know what the solution to this is. We've done the free particle case many, many times. Our general solution is that psi of x is equal to a times sine kx plus b cosine kx, where k squared is equal to 2me over h bar squared. This should all look familiar. It's solving a second-order differential equation, essentially the simplest second-order differential equation you can think of. The subtlety with solving the Schrödinger equation under these circumstances is that the general solution in one sub-region isn't enough. We have to find the solution in all regions, which means we're going to have to match boundary conditions. So it's also useful to know then what the solution is at some other region so that I can match those two solutions together across the delta function. Bloch's theorem tells us that the solution in this region is going to be the solution in this region multiplied by some e to the I k x, e to the I k a, excuse me. Since we're not shifting to the right, we're shifting to the left, it's actually e to the minus I k a, but our solution in this region, psi of x, is equal to e to the minus I capital K a times our solution in this region, a sine k x, x plus a plus b cosine x plus a. So I'm writing now this x is referring to negative values, so I have to shift it over to make it correspond to the values in the other region, and I multiply by this overall constant to make sure everything matches up. So we have our solutions now in this region and in this region, and these are general solutions. We have this capital K in here, which we know a little bit about from the overall periodicity, but we also have this unknown K constant, which is given in terms of the energy. Now, typically, the solutions to the Schrödinger equation matching boundary conditions tells us something about the allowed energies, and that's going to be the case here as well. But these are our two general solutions, and let's figure out how boundary condition matching at this boundary works, since that's going to tell us something about the energy, something about these A's and B's, and so how that information all connects to these capital K's. So the boundary conditions we have are going to match these two solutions together. We have two boundary conditions, and just to recap, we have our delta function potential, x equals 0, and we have our solution in this region and our solution in this region, and we're matching them across the delta function at x equals 0. So the two boundary conditions we have for the wave function. First of all, the wave function has to be continuous. What that means is that psi of 0 plus has to be equal to psi of 0 minus. The solution just on this side has to be equal to the solution just on this side of our boundary. And if I plug these in, the solution for 0 plus, substituting 0 in for x, the sine term is going to drop out, since the sine of 0 is 0, and the cosine term is going to go to 1, since the cosine of 0 is 1. So the b is all I'm going to get. That's all that's left here. This term's dropped out. This term is just equal to b. So my equation then is b is equal to whatever I get when I plug 0 in for the solution on this side. So substituting in 0 for x, the x's are going to drop out. And I'm just going to get cosine ka and sine ka, my a and b, and my e to the minus I ka. E to the minus I capital Ka times a sine lowercase ka plus b cosine lowercase ka. So that's our continuity boundary condition. The other boundary condition that we have to work with is that typically the first derivative of the wave function is continuous. The exception to that typical boundary condition is when the potential goes to infinity, you can have a discontinuity in the first derivative. And the only case that we know of that we can solve so far in this course is the delta function potential. We talked about this when we were doing bound states for the delta function. So if you're fuzzy on how this actually works, I suggest you go back and refer to the lecture on bound state solutions to the delta function potential. Otherwise, the equation we need to tell us how the psi dx is discontinuous relates the size of the discontinuity to the strength of the delta function potential. The equation, and this is equation 2.125 in your textbook, is that the delta of the psi dx is equal to 2m alpha over h bar squared psi. So we need to calculate the first derivative of the wave function from the left and from the right, subtract those two, and that's then going to be related to the value of the wave function and these constants, where alpha here is the same constant that we used to describe the strength of the delta function potential when we first introduced the structure of the potential. So if you actually go through, calculate the derivative of this with respect to x, the derivative of this with respect to x, what you end up with is, well, the derivative for this, we're then evaluating our derivatives at x equals 0, and a lot of the terms drop out. The derivative of this term from the plus direction at x equals 0 is k times a. This is a lowercase k now. The derivative from the left, derivative of this potential with respect to x, evaluated at x equals 0, is e to the minus I capital Ka times a lowercase k from the derivative, and then capital A cosine Ka minus capital B sine Ka. That's the left-hand side of our discontinuity equation here. Discontinuity in the first derivative then being equal to 2m alpha over h bar squared, and the value of psi at 0, well, I could use either the left-hand side of this equation or the right-hand side of this equation, but, well, left-hand side here is much simpler, so I'm just going to use capital B for the value of my equation. Now we have two equations, and we have a lot of unknowns to work with. We have capital A, capital B, capital K, and lowercase k. But it turns out we can come up with a useful relationship just by manipulating these equations to eliminate capital A and capital B. Essentially, what you want to do is you want to solve this equation for a sine Ka. Multiply this equation through by sine Ka so that we have an a sine Ka here and an a sine Ka here. and then use the result of solving this equation to eliminate capital A. So making that substitution, you're going to have a capital B from this equation. So you'll have a capital B in this term, capital B in this term, and then capital B in this term, as before, which means you can divide out your capital B's. So you've successfully eliminated both capital A and capital B from your equation. The subtle term as far as simplification goes is trying to get rid of this e to the minus I capital Ka. But if you make the appropriate simplifications, you can reduce this down not to completely eliminate capital K, but to at least get rid of the complex form of the exponential. You end up with a cosine e to the I capital Ka when you finish solving this. So, subject to a lot of algebra that I'm skipping, the end result here that we can actually work with can be expressed as cosine capital Ka is equal to cosine lowercase ka plus m alpha over h bar squared lowercase k sine lowercase ka. So this is an equation that relates lowercase k, which is related to our energy, to uppercase k, which is what we got out of Bloch's theorem, the strength of the delta function, the mass, and the mass of the particle. This is then going to tell us essentially the allowed energies. There were very few restrictions on the value of this capital K. That was just related to some integer. The equation then, just copying it over from the last page, can be expressed, well, this is just the previous equation. Capital K is related to some integer n, and lowercase k is related to the energy. So if I look at the left-hand side here, what do I actually have to work with? Well, my capital K, think about the set of allowed values for capital K. Cap K, just being related to an integer, which can be positive or negative, is going to have a lot of allowed values. Keep in mind now that capital N here is something of order 10 to the 23, so we have a very large number in the denominator. And we have potentially relatively smaller numbers in the numerator. So capital K is going to have very densely spaced allowed values, going, over the allowable values of n, which are essentially the integers, up to some very large number. So my allowed space of capital K values are densely packed, negative and positive. Keep in mind, however, that my capital K's are being substituted into a cosine. So no matter what I use for capital K, it gets multiplied by A. I'm going to have something between 0, or between minus 1 and 1 for the outcome here. The right-hand side of this equation depends on lowercase k, which depends on the energy. So you can think of lowercase k here as being essentially the energy of the state. So we have something that depends on the energy, and it looks like cosine of something related to the energy plus some constant times sine of something related to the energy divided by something related to the energy. You can simplify these a little bit. In particular, I'm going to redefine the variable z equal to lowercase k times a, which means this is going to be cosine z plus some constant times sine z over z. So I'm going to define beta being equal to, where'd it go? It's going to be m alpha a over h bar squared, leaving me with a ka in the denominator. So my right-hand side now, which is what I'm plotting here, is going to be cosine z plus beta sine z over z. So if I plot my right-hand side for a particular value, in this case I'm using beta equals 10, beta just being a combination of the strength of the delta function, spacing of the potentials, mass of the particle, and Planck's constant, you end up with a function that looks sort of like this. It looks kind of like sine x over x. Well, it does. But this z parameter is now related to the energy. So essentially we have an x-axis here that tells us the energies. And we know we can have solutions whenever it's possible to solve this. Our capital K space, densely packed with allowable values of capital K being plugged into cosine, is going to give us very densely packed values of, well, essentially the y-axis here, whatever the y-coordinate is. Since there are so many allowable values of capital K, since capital N here is a very large number, you can think of these essentially as a continuum of allowable values on the y-axis. The places where I have a solution then are going to depend on, well, the right-hand side of my equation, which is only between -1 and 1 for certain values of the energy. So these shaded regions here, where the energy of the state is such that the right-hand side of this equation corresponds to values between -1 and 1, for which we can find a nearby allowable value of cosine capital Ka, these are the allowed energies. And they come in bands. There is no single isolated value of the ground state energy. There is sort of a continuum of allowable energies, subject to these approximations that capital N is very large, for instance. So if we're dealing with a macroscopic chunk of material, the allowed energy states for a free electron that's encountering these atoms are going to come in energy bands. This is actually a really, really nice result because it allows us to understand a lot of the properties of things like conductors, insulators, and semiconductors. If, for instance, we allowed bound states to exist as well, they would have negative energies. So our free electron states are going to appear in separate bands. Our bound states are also going to appear in bands as well, and you can verify that by going through the solution process using delta function wells instead of delta function barriers. But if we have no bound or no free electrons, if we just have bound electrons, if we just have states down here, essentially, we don't have enough free electrons, don't have enough electrons, period, in this state to occupy all of our possible bound states, then we have an insulator. If we have states populated, again, same as in the previous lecture, starting with the lowest energy and populating states as you go up, you'll have an insulator until all of these bound states are filled. Once you start filling states in this first sort of energy band of free electrons, you have a conductor. It's very easy for electrons in an energy state here to shift to another energy state of slightly higher or slightly lower energy that may be slightly displaced in the conductor. So it's possible for an electron to move from one side of the conductor by moving from one of these free particle states to another. If we have all of our bound states filled and the complete conduction band, or a complete band here, also filled, well, that's going to be an insulator again, because it's impossible for electrons to move from one state to the other if all of the available states are filled. The only way for an electron to effectively become free here is for it to jump up to the next energy band across this gap. So we have gaps between our bands. And that determines whether or not we've got a conductor or an insulator. A third case that you've probably heard of is if we have, well, all of our bound states filled and almost all, or perhaps just a few states in the next energy state filled. This we would call a semiconductor. It can act like a conductor if you have these few extra electrons filling the lowest energy states in a mostly empty band. But if you lack these few electrons, then you've gone to the insulating state. So they're states that are sort of on the boundary between entirely filled and mostly empty. And if you add a few electrons, it acts like a conductor. If you subtract a few electrons, it acts like an insulator. And this transition between conductor and insulator is something that we can arrange chemically and electrically, and this is essentially the basis of all of semiconductor physics. We'll talk in the next lecture about how semiconductor devices like diodes and transistors actually work in the context of these allowed energy bands and what sort of chemical modifications happen as a result. Another note here is that the temperature affects the energies that are allowed here. The next section in your textbook after this talks about quantum statistical mechanics, which tells you about, as a function of the temperature of the material, how these energy states are likely to be populated. The approximation that we're making here by saying start filling the energy states from the lowest energy possible and continue until you run out of free electrons isn't entirely accurate. That's essentially assuming that everything is at absolute zero, that there is no additional energy available to these materials. Now, conductors, insulators, and semiconductors behave differently in the context of temperature. Because, for instance, consider a conductor, or consider an insulator. If I have an insulator like this, or an insulator like this, if I add energy to that insulator, I'm essentially going to be contributing some additional energy to some of these electrons, which would otherwise be filling the lowest possible energy state. So I would be kicking them up to higher energy states. And if I have an insulator like this that hasn't even filled all of its bound states, well, adding energy is going to kick them up to higher energy bound states. It's unlikely to make those electrons free. But if I have a conductor that has entirely filled a sort of free electron state, and I add energy, I may kick more and more and more electrons up to the next higher energy band, transitioning that insulator into a conductor. So if I have an insulating material and I increase the temperature, the conductivity of the material tends to increase. If I have a conductor, on the other hand, and I add energy to these states, well, I'm not actually making any more free conduction electrons. I'm more just rearranging existing conduction electrons. And that rearrangement actually happens to be unfavorable under most circumstances. The classical explanation that's usually given is that as you increase the temperature of a material, the orderedness of the material goes away. Essentially, that nice periodic array of delta function potentials becomes slightly disordered, and that disrupts the band structure and makes it more difficult for electrons to transition from one energy state to the next. Thinking about it classically, the electrons are more likely to collide into atoms that are vibrating rapidly than into atoms that are nice and stationary. So if I increase the temperature of an insulator, I make it more conducting. If I increase the temperature of a conductor, I make it less conducting. If I increase the temperature of semiconductors, you can actually do some math to figure out what's going on. I'm not going to ask you to do that, but if you increase the temperature of a semiconductor, typically you increase the conductivity. So we can understand a lot of the properties of how insulators and conductors, even semiconductors, behave just with this simple periodic array of delta functions, which describes that the results are going to have the resulting energy states that are available for a bound or free electron in this material are going to come in bands. And the relative population of those bands determines essentially the nature of the material. To check your understanding of this, here are a few questions, namely asking you to recall what that trick was to figure out the boundary condition in terms of the discontinuity in the first derivative of the wave function at a delta function. Finally, describe how you suspect the solutions would change if the delta function wells had been used instead of barriers. We used barriers, assuming that if the electron was right on top of the atom, it would be strongly repelled by essentially running into the atom. But maybe it's actually attracted. Maybe there are bound states as well. Finally, going back and looking at that equation that gave you the energy bands, how do the energy bands look? What is their spacing? How wide are they, etc., as the energy becomes very large? And finally, there's this essay that's intentionally humorous, Electron Band Structure in Germanium, My Ass. I'd like you to read through that. It's fun. I'm not actually asking you to do all that much here. And that explains qualitatively what the plot that he describes should have looked like.